Our event for the evening is a chat between myself and Jonathan, which might have the subtitle of I'm trying to understand what Jonathan's been up to for the past several months, which can sometimes be challenging. But I think what I'd really like to do is talk about some of the things that I know Jonathan's been working on, and maybe my kind of mundane questions will help illuminate some of these things for everybody. So if I understand correctly, people talk about categorifying things. Mm-hmm. And could we say that that part of what you're doing is categorifying multi-computation? Would that be a reasonable thing to say, or is that way off base?
No, I think that's a pretty reasonable way to phrase it. I mean, in a sense, one of the reasons I wanted to have this conversation, or I thought it would be useful to have this conversation, is like I kind of feel as though both of us, in slightly different ways, are trying to kind of investigate, the abstract science of multi-computation and its various applications. And people often say that sort of category theory is like a mathematical language for processes and how processes compose. But in the modern world, the standard way that processes get represented is as computations. So I think in many ways it's more fruitful to just think of it as being a mathematical formalism for computations and how they compose. And in a sense, ordinary category theory where you just have sequential composition is basically akin to classical theory of computation. Monoidal category theory, where you can do composition both sequentially and in parallel, I view as being like the kind of categorification, as you put it, of multi-computation and multi-way systems. And so, yeah, to a great extent, what I'm trying to do right now is make that connection a bit more concrete, develop the formalism a bit further, and see how some of the areas in which we've been attempting to apply multi-computation so far, like in physics or in chemistry or to foundations of mathematics, how those can be potentially informed by this connection to compositionality.
I'm excited. Okay, so let's go into this in more detail. So first of all, for everybody's benefit, let's just start off by talking about what is category theory. What's the maybe everybody knows that. Does everybody think they know that here? Or some Yorick is saying yes, but that doesn't count.
I've talked about nothing else for the last couple of weeks.
Oh, is that right? Right. Well, for my benefit, perhaps, can you say what you think? What do you think at this point, now that you've studied category theory and monoidal category theory and so on? What is the essential idea of category theory?
Okay, so in a sense, the way I like to think about it is that the set theoretic picture of mathematics involves, you can ask the question, what is a mathematical structure, right? You give me some group, what is that group? You give me a topological space, what is that topological space? The set theoretic perspective says, well, we just break it up into pieces. We look at, for a topological space, we look at its point set, or for a group, we look at its group elements. And we get some notion of identity of that structure from, breaking it up into pieces. Category theory, I think, is a more relational, more process theoretic, ultimately more computational way of answering the same question. That you say, no, instead, you don't want to look inside the object, right? You don't want to break the group up. You don't want to break the topological space up into points or into elements. What you do is you say, well, what gives this structure its identity is how it relates to all other structures of the same kind. So, so if you want to identify a particular group, another way you could answer that question of, what is that group, is you can just say, what other groups does it have homomorphisms to? What other groups is it isomorphic to? How does it relate to all other groups in the category of groups? And that's effectively or similarly with topological spaces. What other spaces, instead of talking about points and point sets and topologies and open sets and things, you could just say, well, what other topological spaces can this be continuously deformed into? What other spaces can be continuously deformed into this space? And if you give essentially, the collection of all continuous functions to all other topological spaces of the same kind, the remarkable feature about compositionality is it's an equivalent answer to that question, right? The same information you get by breaking the topological space up into pieces is also captured by the information about how it can be, continuously deformed into other spaces.
So let's take that apart for a second. So let's take a simple example. Actually, right. Let's take an unreasonable example. Let's talk about Turing machines. Mm-hmm. What is the category theory view of Turing machines?
Well, okay. So Turing. So one thing that's definitely one very interesting general feature of category theory is that, and this is really, more concretized in topos theory, but we can just stay at ordinary category theory for now. That it makes this there's this duality, or more precisely what's called an adjunction, between sort of between syntax and semantics, effectively between, if you give me a formal model of computation, generally people talk about this in terms of type theory, but there's no particular reason to talk about it in terms of, it's just that happens to be the approach that was adopted. But if you give me some formal model of computation, I can construct a category, which is really just a multi-way system that encodes the syntax of that computation, right? So, for the case of a Turing machine, I can construct some multi-way system where, every state vertex is a Turing machine state, a state of a tape and a state of a head, and every evolution edge is is the application of some Turing machine rule. And obviously those different threads of Turing machine evolution can compose sequentially, and they can compose in parallel, and that's what gives you kind of the structure of the multi-way evolution graph. But there's also a kind of semantic view of what's going on, which is that you can talk about this, in the case of Turing machines, you could talk about the partial functions that Turing machine is computing and how they relate to it. You can effectively, you can imagine instead a semantics on the category of sets and set valued functions. And then there's this very nice relationship where you can define a pair of functors that take you from the kind of syntactical category to the semantic category and back again.
Let me try taking
sorry, please.
My simple way of thinking about this. Okay, so in a multi-way system, we have the nodes of the multi-way system are states of Turing machines.
Right.
And then there are, in some rulal multi-way system, there are multiple possible rules that can be applied from every state of the Turing machine to make new states of the Turing machine.
Right.
So we have this time evolution of Turing machines going in this multi-threaded time evolution of Turing machines.
Mm-hmm.
So that's our standard sort of multi-way story.
Right.
Now you say there's a dual picture, which is consider the functions that Turing machines compute.
Right.
Right. So we have to define a little bit what we mean by what functions a Turing machine computes, because that's imagining, we've got in this original view of multi-way systems, we've got a particular state of the Turing machine evolves to a particular state of the Turing machine.
Right.
How do we get to, so a function, it means you've got a whole range of possible initial conditions for the Turing machine, mapping to a certain range of possible final conditions.
Right. Right.
So we've got a bunch of different dots in the multi-way graph, and we've got their kind of, how they flow through to a bunch of other dots in the multi-way graph. So
right.
Is that the right way to think about it?
Yes, yeah, absolutely. And so in a sense, okay, I mean, we're skipping maybe ahead a little bit, but that duality between syntax and semantics has a very concrete realization in the context of multi-way systems, because effectively the semantics is given by branchial graphs and mappings between branchial graphs. And so maybe Turing machines is a bit of is a less nice example to get your head around. I mean, so the example I might give that's a bit less sort of mind-bending would be something like groups, right? So you can build a multi-way system, multi-way operator system or something that encodes the axioms of group theory, right? And so you just start from some seed, and in principle, every proposition that's true about, in universal algebra about group theory will exist as some state vertex in that multi-way system. But you could
you say that very quickly, but I think it's a little bit more. I mean, there's more to say there, right? Because you're saying, well, let's not give up on the Turing machines for a second.
Okay.
Because you're what you're saying is there's this notion, which I like very much, of this the function computed by the Turing machines is this mapping of this whole collection of possible states, which could be a particular slice captured by a branchial graph, mapping to another whole slice captured by a branchial graph.
Right, exactly.
And that the branchial graph to branchial graph mapping you identify as being the function defined by the Turing machine, as opposed to the kind of the individual path followed, which is the actual the execution of the Turing machine.
Right.
Okay.
And so actually the syntax semantics duality is deeply related to this sort of fibration foliation duality. Right.
Okay, so but I'm not wild about this notion, this term syntax versus semantics, because I've spent so much of my life in computational languages.
Okay.
Semantics has a whole bag of other issues. But in the case of so what you're saying is we can think of this collection of this multi-way collection of Turing machines as being in terms of every thread of evolution. Mm-hmm. We can also think about it by saying we take all the possible states of the Turing machines at a particular quotes time,
yes,
and we look at the mapping of that whole collection of things onto some future state.
Mm-hmm.
Okay. So
actually, I mean, sorry, just on that point. So I agree in some ways using the terminology syntax and semantics may be unnecessarily obscure or something. But how would you? I mean, so it does seem to me that there is an inherent distinction between, you've got some bare metal multi-way system that's just producing a bunch of states. There's then some interpretational or encoding step where you say, and this computes such and such a function. And how would you, just terminologically, how would you distinguish the bare metal multi-way system from the kind of interpreted one?
Well, when you say interpreted here, we've got this whole giant branch graph, which is something that, in our view of the observer, is something where the observer has to be the thing that's knitted together this whole collection of different, as you're putting it, bare metal computations.
Right.
And I suppose that concept of an observer to observer, observer state to observer state transformation.
Yes.
I mean, for me, that's sort of a new concept. I mean, in the sense that I'm not sure that I would associate that with, when I think, okay, let's talk about syntax versus semantics as it's described in languages.
Okay.
I mean, so the syntax of English is, how do you put the words together? The semantics is what is the quote inner meaning of that piece of English?
Right.
The problem is people have always had a hard time understanding what on earth inner meaning actually is. We finally have, with Wolfram language and the whole computational language idea, we now have a sort of, for me, I see that as a concretization of what inner meaning actually is. But I don't really quite get there are many syntaxes, many ways I can say a sentence, which map to the same inner meaning.
Right.
And presumably, and somewhat obscurely, there can be a sentence that can have a particular syntax that can be interpreted with many different inner meanings.
Right, which is semantic ambiguity. Yeah.
Yeah, which is depends on who you are and where it's said, all this kind of thing.
Or how even things as mundane as how the sentence is parenthesized or whatever. Right. I mean,
yes.
Yeah.
When you say, I'm doing this, blah blah blah, or I'm doing this, and your voice goes up at the end, and it's a question.
Right. It's neither injective nor surjective as a function.
So these are two separate, and I don't quite see the analogy between kind of the syntactic level is an easier to define structural level. The semantic level is this thing that's operating above that I've always found very hard to define.
Right. I mean, in a sense, that's actually why I brought up the example with groups, because I think generally in foundations of mathematics, I'd say the distinction between syntax and semantics is slightly better defined because you have this distinction between proof theory and model theory, which is quite a hard distinction. So I know that we disagree on this.
No. I mean, the fact is, one of the questions is, what is mathematics actually about?
Right.
And Hilbert famously said it might be about tables and chairs. It doesn't really matter. It's just a formal system where you set up the rules for the formal system and then you prove things from it. Whereas other people, like I guess who was Poincaré, for example, was very much, no, it's not just about tables and chairs. It's about things we actually imagine are somehow real in some Platonic sense.
Or famously, right? I mean, that actually influenced Gödel's research, right? I mean, yes. he thought showing, for instance, that there existed models that were consistent with the continuum hypothesis was equivalent to showing it was true, which is only really acceptable if you're a Platonist.
Well, Gödel was very much a Platonist. I mean, Gödel,
that's what I'm saying.
As I only learned quite recently, the usual picture of kind of the Gödel operation was, there was Hilbert who was trying to define this model where, mathematics would all become mechanical. You just had to set up the axioms. And then as Poincaré described it, critically, he said, you're turning mathematics into a thing like this machine I've heard about in Chicago, where pigs go in at one end and what was it, hot dogs?
Yeah, sausages, yeah.
At the other end. And that mathematics is then turned into just this machine where you mechanically go from the underlying axioms to everything that might be true. And that was kind of the view of mathematics in the first few decades of the 20th century. And then, the usual picture is Gödel came along and said that can't be right because there are these undecidable propositions, these things that can't be established with finite proofs by the machine, where the machine would never actually produce the sausage, so to speak. But I think what I recently learned is that the picture was Gödel was operating within this framework of this very mechanical view of mathematics. But actually, Gödel, he has this one footnote where he says, well, this might be true that there are these undeterminable, propositions and things. This might be true, but for brains, for human minds, things might work differently. And I think what I've only learned recently, maybe other people knew this all along, is that Gödel really had a very Platonic view of mathematics, that there really is an underlying to mathematics, and that all of this stuff with Hilbert's, axiomatic framework and formalism and so on was merely an attempt to kind of provide a set of mechanical accesses to that, but there was something different and fundamentally different underneath. And so he thought that by showing that this sort of formalistic wrapper was going to blow itself up, that would establish that there really was something underneath in some Platonic sense.
So I have a couple of comments on that. I mean, one is, so there's a version of that argument which is, attributed to Gödel, but which is kind of made a little bit more, maybe a little bit, phrased a bit more eloquently in some of Roger Penrose's writings, where he also defends the Platonist position, but essentially using a modification of that Gödelian argument, which is that as far as I can tell, both Gödel and Penrose have the same kind of philosophical interpretation of Gödel's second incompleteness theorem, the statement that you can't prove the consistency of piano arithmetic from within piano arithmetic itself. So, essentially a version of the argument, okay, there's a lazy version and there's a slightly more sophisticated version. The lazy version of the argument is, but we can see that, arithmetic is consistent, and therefore we must be doing some process that's not captured by this formal specification of the machine that's doing the proving. A more interesting version of that argument is you say, well, the fact that one of the things that theorem tells you is that in effect there's now this whole infinite hierarchy of arithmetics, because if you have piano arithmetic, you can always construct a stronger system, which is piano arithmetic plus the axiom that piano arithmetic is consistent, or that axiom system plus the axiom that system is consistent, and so on. And so, the argument goes, well, for any attempt you make to kind of to box mathematics in, to formalize it in some finitary deterministic way, there's always some way that it's going to be able to break out of it again, which again is kind of viewed as a defense of the Platonic view. I know you're aware of this, and I know we've discussed this in some detail, but maybe it's worth saying, just in case it kind of wasn't clear to other people, that one of the things that comes out of, well, NKS, and I'd say more recently from the physics project, you have notes in the Foundations of Mathematics section of the whatever the Principle of Computational Equivalence chapter of NKS to this effect. But this distinction between the sort of Gödel view of Platonism, the Hilbert view of formalism, the sort of Russell-Whitehead view of logicism, etc., that those distinctions kind of evaporate when you start to think about science and mathematics in more explicitly computational terms. In no small part because if you take something like the Wolfram model, right, it's in its most abstract form, it's just a collection of rewriting operations on hypergraphs or collections of elements, and those elements have no intrinsic meaning; they're just purely symbolic, right? And I realize you have this kind of term "eames" to sort of refer to this in the more.
It's now being captured in a fine science fiction novel that somebody is writing.
Right.
So it's real now.
Right. But so. If that is a good model for science and for physics, then one is confronted with the realization. So Hilbert famously defended this formalist position by saying that mathematics is nothing more than this meaningless game played with meaningless symbols on bits of paper. But if we now have to confront the possibility that our universe is a meaningless game played with meaningless symbols on, well, presumably not bits of paper, but on some as yet undefined substrate, then you're forced into this rather awkward philosophical position of either you have to afford physical and mathematical objects the same degree of ontological, substance, or you have to kind of argue that this is the wrong way to view, the structure of reality. And so in a sense, it when taken to its logical conclusion, I'd argue, and I suspect you'd argue too, that it really means that that Hilbert's version of formalism also implies a version of Platonism.
I suppose you could say that. I mean, my argument would be we're forced to a position where if we say we exist, we also have to say mathematics exists.
Right. Or physical objects exist, or whatever.
Right. Yes.
Either nothing exists or mathematics has to exist.
Right. It has to fundamentally exist as a sort of a thing that you can it's not something where you're just defining it formally. It's an inevitable existing thing, so to speak. But I think we kind of diverted here.
Sorry.
Syntax semantics.
The point I was going to make in relate, you were disagreeing with my statement that the distinction between proof theory and model theory is rigid.
Whether we can have in our imagination, whether the integers are a real thing, or whether the integers are merely a. Maybe you should go on with your.
All I was going to say was that so you can imagine. To take this back to something more concrete and computational, you could imagine having two different kinds of multi-way system, right? You could imagine having multi-way systems that are effectively multi-way operator systems based on the group axioms. And you could also imagine having a multi-way system where every state vertex is a group and every evolution edge is say a homomorphism. And that would be, so in the, in this adjunctive relationship in category theory between type theory and models for type theory, you would call the first thing the syntactical category and the second thing the categorical semantics. And the interesting thing is that you can generate one from the other, right? So there's a pair of left and right adjoint functors that take you from, I mean, again, the standard way you describe it is that you've got a category that represents a type theory in which every object is essentially a type environment, and every morphism is a kind of a replacement of, is a substitution, as a replacement of variables. And then you've also got this other category which is like the actual semantic thing where the objects are groups and the morphisms are homomorphisms or something. There's a sort of procedure that will freely generate, say, the semantic category from the syntactical one, and you get this thing called a walking model. And so it's a fairly, I mean, there's a lot more that needs to be kind of concretized, but it's a fairly well-developed sort of idea.
This apart.
Yeah.
This is interesting. And okay, so, on one picture here is you've got a multi-way system where every node is a whole group.
Yep.
And every edge is something that connects that group to a group to which it is homomorphic.
Yeah.
Okay, that's thing number one. That's your sort of semantic level version. Now you've got a level where the individual elements are what how are you constructing your syntactic level thing? What are the pieces of the multi-way system in that case?
Well, so for the case of so this is an algebraic, group theory is an algebraic theory, which, and kind of what it means to be an algebraic theory is that you have some binary operation and you have equational rules. So probably
words.
Right. But generally words that are quantified, right? They're not specific words in some model of a group. They are universal algebraic statements.
So hold on. When you say statements, okay, just for clarification, right? So groups, you can. I mean, this is something in that mathematics piece I did. Was something that held it up for a year and a half. Was the sort of messy correspondence between a theorem being something which is this word, this set of symbols is equivalent to this other set of symbols, versus a theorem which says this set of symbols is equivalent to this set of symbols, and deriving another equivalence from that first equivalence.
Right.
Those two things are not fundamentally different. One is just applying rules to elements, and the other is applying rules to rules, effectively.
Right.
They're not fundamentally different, but I'm just to clarify it, maybe it doesn't matter.
Well, but this is why I brought up the thing about algebraic theory. So in an algebraic theory, I would argue the most natural representations have every state vertex be an equation, and have every evolution edge be an application of some equational, a one-way application of some equational rule. Whereas in more general non-algebraic theories, it makes more sense to have each state vertex be a proposition, and then have the evolution edges effectively be one-way implications.
Fine, but what you're saying is you've got an equation that says A dot B equals B dot A dot A or something.
Right.
And then you have a transformation which turns that equation, which potentially is another equation applied to that equation, where you substitute one equation into the other, and you get the result, B dot B equals A dot A or something. Right. And that's okay. So we've got this notion. So in the token event graph formalism, for example, we will be saying that these tokens are equations, and that the typical sort of rule of evolution, the law of inference, rule of inference, is two equation tokens, kind of mixed together, and one is substituted into the other, and you get a new equation out of them.
Right.
Is that the kind of picture
Right, something like that.
Okay, fine.
And so then in effect, that sort of syntactical multi, I mean, again, we may want to cover proof theoretic multi-way system is essentially defining, it's, as any multi-way evolution graph is, it's defining some partial order on the state vertices. And that partial order is essentially telling you what you can deduce from what, right? You've got, if A precedes B, then it means you can derive B from A.
It's a little bit more complicated in this case where you're applying, where there are two equations coming in, they get mixed together and make one equation out. Because things are going to be reversed. I mean, these equations get reversible and so on.
Right, but that's why if in effect your state equivalence function has to take into account these things like paramodulation that deal with things like rule orientation. But
right. I mean, what you're saying there is when you take one equation and you apply it to another equation, there are a bunch of weird little pieces of knitting that you can do as you apply one equation to the other.
Right.
And that, substitution, bisubstitution, co-substitution, paramodulation, which is, I think it's the same as bisubstitution, but I'm not sure. These are all just complicated things about which variable is replaced and et cetera, et cetera, et cetera. But we've got something where we have theorems effectively in the system that are derived from other theorems.
Right.
And you've got some path of theorem derivations.
Mm-hmm.
And that's view number one. And you're saying view number two is you're taking a thing that's formed from a collection of theorems, or that for which a group is a thing for which a bunch of theorems are true.
But okay, crucially though, a specific group, what distinguishes doing group theory in relation to a particular group from just doing universal algebra, right? From just proving statements about groups in general. Well, the key difference is that for a specific instance of a concrete group, there will be additional theorems that are true about that group, which are not true in the universal algebraic case. So effectively what you're doing, one way you can think about it, is that you're taking this partial order that your syntax multi-way system, your proof theoretic multi-way system defines, and you're making it more like a total order, right? You're introducing new orderings between states that were not true in the existing multi-way system. So,
or another thing you could say is, of all of those relations which were there, only some subset of them are now considered true for this group. So you're taking a slice out of this whole complicated network of theorems. There's some bag of those theorems that's true for the group.
Well, no, but every theorem that's true in universal algebra is obviously going to be true for any specific group.
Yes.
So it's more that it's not that you're removing some theorems; it's that you're effectively introducing new ones.
Right. There are additional theorems which are true.
Right.
You're saying, and those.
And so you can make the analogy to relativity when you've got the conformal structure or the causal structure of space-time that is kind of a universal thing, and then individual observers impose new a particular observer can introduce new causal, new chronological relationships between space-like separated events.
Well, or in particular, they can choose. This is simultaneity.
Right. Right.
Which is to say.
And the point is that in the degenerate case, as you approach the speed of light in the relativity case, your space-time partial order becomes a total order. Right. That's the degenerate case. So one way you can think about boosts is that it's a way of taking this partial order and making it more like a total order.
Let's walk through the total order. So you're saying that normally you have a bunch of events happening in space-time.
Right.
And if the claim is, if you're a photon, there is only let's walk through this. So normally there are things that happen in different places in the universe, and you get to define whether, what counts as simultaneity. What was, noon on Earth, noon on Mars, when were these things relative to each other?
Right.
Okay. Now, I think you're claiming that if you're a photon, you don't get to do that.
Well, photons have no notion of space, right? That's the basic point. Or time.
Right.
So what does it mean to say that you're undergoing a time dilation or a length contraction? Well, what it means is that effectively your antichains are getting shorter and your chains are getting longer. And if you take that process to its conclusion, eventually everything is just a chain. So the maximum boost is the case where your space-time becomes totally ordered.
Okay, so your claim is when you're using up all your computation on kind of on going as fast as possible, you don't get to move at all in space. Is the basic claim. You don't
Something
get
like
to,
that. Yeah.
Right. You everything is. I'm still not quite internalizing that, but okay. But so. All right, so now you're going to tell us what the analog of that in mathematics is.
Well, so as I say, I mean, just abstractly, all that you're doing is you're taking a partial order and by foliating it, by constructing these equivalence classes, you're just introducing new relations that didn't exist before, which is what happens when you define a model in a mathematical theory. Yes. So one way that you could think about a model is that it's taking this proof theoretic multi-way system and it's foliating it in such a way that you introduce these new relations that didn't exist, that exist only as a consequence of the model that you've chosen.
Yes.
Okay. And that's essentially the branch graph story, right? That's now you're viewing the multi-way system in terms of its branchial decomposition for some reference frame. And so that leads to this rather interesting realization that essentially this duality that exists in category theory between, I know you don't like syntax and semantics, but proof theory and model theory or whatever, the syntactical category and its sort of compositional semantics, that's really just a special case of this duality between looking at a multi-way system in terms of its multi-way evolution graph and looking at it in terms of its decomposition into branchial graphs, right? We know that they encode essentially the same information, except the branchial graph also has this additional thing about, it's observer dependent. And that's really that's what model theory is about. And then, for instance, something like the first incompleteness theorem just becomes a statement that, one way you can phrase the first incompleteness theorem is that, in any formal system that's sufficient to encode Peano, is sufficiently strong that it can encode Peano arithmetic, there will be propositions that are true in some models and false in others. And so that becomes essentially a statement that, if you make, again, going back to the relativity analogy, that's equivalent to the or analogous to the statement that there can exist space-like separated events where, A precedes B in one reference frame and B precedes A in a different one. So effectively, the first incompleteness theorem becomes a statement of gauge, essentially a statement of gauge freedom, which is.
Although the other piece to that has to be something about how they're infinite length paths. So how does the infinite length path story and the non-finiteness of proofs, how does that come into that version of thinking about things, that there exist different models? Why is it the case that, it must be something about how you can always find a different model which has this different ordering, and that must be related to the fact that there are these infinite potential proof paths.
Right, so in a sense, if there's an infinite proof path between two propositions or two state vertices, then for any finite size of multi-way system that you compute, they're going to be treated as they're going to be treated as unrelated by the order. Mm-hmm. And so, eventually, if you could take some infinite limit of the multi-way system, they would no longer form an anti-chain. But the point is that, for any finite length of computation, you still have that gauge freedom to choose one to precede the other in any way you like.
You might be, another way to say this is, you think you've got a valid model, but actually, if you were to go long enough in the multi-way graph, your model would blow up because the thing wouldn't actually be consistent anymore, that you could take that as an anti-chain.
Right.
No, it wouldn't actually be an anti-chain. It wouldn't actually, but for people who don't know this lingo, anti-chains just means you have a partially ordered set. Things, you're saying something precedes something, et cetera, et cetera, et cetera. There's a chain which goes, A precedes B precedes C and so on. An anti-chain is just the transversal of that, where you're saying what doesn't have a particular ordering that it needs to, what doesn't have its ordering defined, what can be sort of at the same time as something else. Maybe there's a clearer way to say that. That was a bit of an obscure, and it's basically the transversal to a chain. A chain is what has to precede what, and an anti-chain is what doesn't have its ordering defined for it.
Right. It's the stuff you have freedom to choose, the precedence relation for.
Right. But okay, so let's come back to this groups thing. So mm-hmm. you're saying you've got, maybe the general point, that is that, you can look at branchial evolution, or you can look at the underlying, essentially temporal evolution. In a sense, it's the spatial slices evolving to spatial slices, or it's the individual sort of threads of time evolving.
Right.
And which you are going to interpret as foliations versus fibrations in all sorts of systems.
Right. Right.
Which is quite lovely. But again, you were about to say the interpretation of the speed of light, of the infinite boost in mathematics. I know you've had a version of this for a while. If we imagine in mathematics, we've got these different models that we can take, and they correspond to these different foliations, and then we've got this extreme model where you've tipped things to the point where there are no anti-chains. Right.
So it's
your interpretation?
Well, it's formally the opposite of a free structure, right? So ordinarily in mathematics, you would say, if you talk about, say, a free group or a free ring or a free whatever, what you mean is this structure contains no additional relations beyond just what is imposed by the axioms of the theory. So that's the analog of of the rest frame, right? You just there are no additional relations beyond just what the syntax of the theory implies. The infinite boost case, for which I don't want to claim it doesn't exist. I'm not aware of any standard terminology for this in mathematics. It's kind of the maximally restricted version of the structure. It's as far away from being a free structure as you can get. It's introducing all possible, obviously there isn't a unique maximally restricted structure, right? Because there are many different directions in which you can apply your boost, so to speak.
So is it something for which all theorems are true? A free group is something for which very few theorems.
No theorems are true beyond beyond what's implied by the axioms of group theory.
So maybe this extreme case is sort of all possible theorems are true.
Except it can't be all possible theorems, right? No, it would still be consistent. You'd still want it to be a consistent theory.
Yes, but it's still the case that you are adding an infinite collection of relations.
Right.
I think you're figuring something out.
No, I'm just asking, can you briefly explain why that is well defined?
Why the sort of
the opposite? So your infinite boost object, whatever you call it, why is that a well defined?
And is it
no, I'm not.
I think it's probably not.
Well, I'm not claiming that it's well defined.
Okay. Yeah.
In fact, that's the point I was making about just like with boosts, there are infinitely many directions you could apply your boost in. It's just effectively you're somehow it's some sort of optimization problem where you're maximizing the number of theorems that are true about this particular structure. And I don't think that's.
Let's nail that down a little bit more carefully. This seems interesting. So what's the analog? I mean, the free group, free any algebraic structure. What's the simplest case? What is the simplest case of this? The simplest case is there are no relations.
Right. So in group presentation theory, it has your presentation has generators but no relations, right? So it's just a freely generated group.
No, I understand. But you forget the group part of it. If we just have something where
it's
a pure binary operator,
right,
it's just hanging out and doesn't have any particular relations at all. That's the case. The free case there.
That's a free magma, I think.
Okay. Is that what? Okay. So that's all right. So in that case. Is that what a magma is?
I can't remember. I think that's. I think
magma had some.
Magmas have closure and nothing else. I think if I recall.
Okay, but all right. But so it's just this thing. It's got a binary operator, but there are no relations that are true. So its free version has no theorems.
Mm-hmm.
I think maybe it has a theorem that A equals A, and maybe that's something to do with this closure property, or the thing is equal to identical thing.
Well, yeah. I mean, there are things that are true. This is in effect what paramodulation is about in equational theorem proving. It's about there are certain statements that are just structurally true by the nature of equality being an equivalence relation. So A equals A, it's reflexive. If A equals B and B equals C, then A equals C, and that kind of stuff.
So the free case is just identical things are equal to identical things, and nothing else is true.
Well, and as I say, you have the standard properties of an equivalence relation, right? You have transitivity and
well, but that's not going to say very much. I mean, transitivity is just saying the identical thing equals the identical thing equals the identical thing. It's not saying A equals B, B equals C, therefore A equals C, which is the usual transitivity relation. There isn't any such relation because it's only saying identical things are the same as identical things, isn't it?
Why?
If there are no relations, if there are absolutely no relations, all you can do.
Then you may not be able to distinguish.
Yeah, right.
If that's what you're saying, okay.
Right. Okay, so now that's the absolutely free limit. Now, what's the take that and start adding relations. So the relations you're going to add are expression equals expression for all possible expressions. So eventually the thing will be gummed up to the point where, first of all, it thought everything was free floating and it had no relations to anything else. And then eventually it just makes a single big blob where everything is equal to everything.
Right.
So then the end result, so you're saying the boosted thing is an everything equals everything type situation.
Yes.
So that's saying that in a sense, there's no, what is that really saying? From a proof theory point of view, that says that everything is connected to everything. You've got this giant, your multi-way graph is just this, what is it? It's just every node, it's a complete graph. Every node is connected to every other.
True equal false too.
Right. I mean, yeah, normally you'd want it to be consistent. So in particular, you shouldn't have, you shouldn't have cycles where you can.
But what is consistency for universal algebra? Isn't that a different story? I mean, you can't, in other words, the notion of consistency is a different thing from these algebraic theories. The notion of true and false doesn't enter as such. I mean, a group, true is not an element of a group.
No.
The group just has words.
Mm-hmm.
And so, but I think, okay, so what you're saying is, I mean, the basic point, ignoring the true false thing, which I'm claiming you can ignore when you're thinking about things algebraically. What you're saying is that in the extreme boost, the extreme model is the model where you've poured in every possible group relation, for example.
Sure.
And therefore everything equals everything.
Mm-hmm.
And so how should we think about that? How should we think about that? What the heck is that? That's as you get closer to that limit, okay, is that the same thing as saying that for a photon, time never passes?
Well, it's certainly related, right?
I think it is.
Yeah.
I think because for a photon, it sees the whole history of the universe. For a photon that was emitted, 100,000 years after the beginning of the universe, and we just catch it in the cosmic microwave background. For as far as it was concerned, it was just emitted, and we just, and it ended its time in that random detector. But so what this is saying, I think, is that okay, so time never passes for a photon because it is seeing in some sense the whole history of the universe in one moment of its time. It's seeing the whole history of the universe.
Mm-hmm.
So similarly, in this completely connected, algebraic system, in one relation, it is seeing every part of the algebraic system.
Mm-hmm.
I think that's right. I mean,
yep.
So in other words, time in the algebraic system, we can think of time as being proof steps,
mm-hmm.
right? And what this is saying is there are you can get to everything in one proof step, just as in the photon, you can get to everything in one moment of time.
Okay.
So, okay, I'm not sure where we were going, but that was actually very interesting. The correspondence between sort of the infinite boost in mathematics becomes, I mean, what is our interpretation of that? The infinite boost in mathematics is that everything is instantly true, I think.
Mm-hmm.
I'm not sure if that's just like everything. Yeah, okay. But anyway, I'm distracting because the original prompt was so you're categorifying multi-computation.
Right.
So I want to, but you were making a point about mathematics, which I think I derailed.
Sure. Oh, by the way, so Tyrus, did you have your hand raised?
Yes, one question about the notion of having a group and putting in all the compatible group relations we can have.
Mm-hmm.
As a matter of fact, isn't this what we will get? Isn't this answered by the categorization of the groups? Because this categorization tells us all the possible groups we can have. So no matter how many relations we throw in, it should be something of all.
Right. And I mean, for the particular case of groups, I think Dugan has already pointed out in the chat that it's the up to natural isomorphism, it's the trivial group, right? Because if everything's equal to everything, then everything's equal to the identity. So it's
throwing in relations doesn't mean that everything's related to everything, because one relation will use one structure, another relation with another structure, and these structures may not be compatible with each other. But the things of all the set of all things we can get must be something among the things that can be categorized as what can be groups for a particular order. So
I don't think so. Once you throw in enough relations, It's just got to relate everything to everything, doesn't it?
Right.
I think.
I mean, you can run this experiment. If you run multi-way group and you just add more and more relations, the states graph will become more and more connected.
Yes,
right?
but
So
what I'm saying is that when you throw, for some three relationships, they don't have to hold, so to speak. If something is equal to one relation, it doesn't have to be equal to the other relations. It's just in three groups, three different groups. And this can be isomorphic, it can be different structures.
I want to come back to this correspondence between the multi-way system where it is theorems, where the nodes are theorems, and where the nodes are groups.
right.
Because that's what you, in some sense, maybe that's at the heart of this notion of categorification, is that you made the statement that the original multi-way system, it might be the case that nodes are theorems, and then you can make a correspondence between that, and I don't understand this, so I'm trying to understand this. You can make a correspondence between that and a multi-way system where the nodes are whole groups.
Right. Right.
Okay, so can you explain that? So the first multi-way system is just the universal relations about groups. It contains all the universal relations about groups.
Right.
And now you say, what is the correspondence between that? Given that, you're saying, I mean, each blob in the thing which has particular groups has had additional relations thrown into it. So each blob could be labeled by its additional relations.
Right.
Is that true?
Yes. So again, this is why it relates to the duality between multi-way evolution graphs and branch-hill graphs. So the multi-way view of what's going on is you define, you take some multi-way evolution graph, you define a model, it produces a sequence of branch-like essentially a sequence of branch-hill graphs. Then you could imagine treating that sequence of branch-hill graphs as a single thread in some other multi-way system.
Yes.
That's effectively acting on branch-hill graphs.
Yep.
But you could also consider, but that's just one possible sort of foliation of the original multi-way system. There are many, many different foliations.
Actually, I'm confused already at that point. In order to get from the original giant, you've got this multi-way system. It represents all possible theorems you can derive from pure group theory. Okay. Now you take a branch-hill graph out of that. It's a slice across the whole multi-way system at some time step, basically.
Yes.
Okay, so now I don't understand the statement that you're taking that those branch-hill graphs can be rolled up into single nodes, because that branch-hill graph extends over the whole space, doesn't it?
Of course, but that's why it's a different multi-way system that you're constructing, right? I mean, again, it's analogous to the power set construction in something like in non-deterministic computation, right? When you convert a non-deterministic finite automaton to a deterministic one, you're defining the deterministic finite automaton as acting on the sets of permissible states of the non-deterministic one. Okay, so in the same way, you can compress any multi-way system into a single-way system that's acting on the branch-hill graphs of the original multi-way system. That's the generalization of the power set construction.
Okay, so
right?
let me go through that for a second. Slightly more slowly. Okay, so you have this multi-way graph, and you can say, I can summarize what happens in this multi-way graph by just taking these spatial slices, which are the branch-hill graphs. And there is a single way story because it is just one thing goes to, you start at the beginning, you have a branch-hill graph that slices across the whole multi-way system, goes to another branch-hill graph and so on. But if I'm understanding correctly, you're saying, but actually there's another thing I could do, which is instead of looking at that single way evolution of one branch-hill graph with that, in this particular foliation of one branch-hill graph to that branch-hill graph,
right?
I could consider all possible foliations.
Right.
And that is a different encoding of the multi-way graph,
exactly,
which is the mapping from all, a branch-hill graph as defined by some weird foliation.
Right.
And all possible, you make a branch-hill graph with that weird foliation, it will map to another branch-hill graph in another weird foliation, in another weird transversal slicing. And then you can make okay, so this leads to the question of, there's a function that like Nick wrote, and maybe you have a version of this function as well. This will simply take a multi-way graph and turn it into this dual branch-hill, or maybe not, maybe it isn't Nick's function, I'm not sure. But so it should be the case that you could write a function which will take a multi-way graph and simply turn it into its corresponding branch-hill multi-way graph.
Yes, I do. Yeah.
Do you have such a function?
I have code that does that. Yeah.
Okay.
So
what is that? I never thought about that function before, I think. Maybe I already did in some other world or situation, but okay. So what you're saying is, but now how do you parameterize these weird foliations? Are they parameterized by by adding relations. In a mathematical sense, you can presumably parameterize them by saying what relations you add.
Right, exactly. Yeah, in effect, what new orderings between state vertices are you introducing, which is another way of saying what relations are you adding.
So by ordering between state vertices, normally it will be a slice where you've got simultaneity, so to speak, defined like this, but sometimes you want to have your simultaneity surface go up.
Right.
Turn what was previously a time-like connection into what was previously a space-like connection into a time-like connection of some kind.
Something like that. I mean, the point is that the rest frame is like the free case, and then anything that's not the rest frame is going to introduce new relations.
Or anything which has a gravitational field, effectively, because it's bumpy.
Yes.
But
it doesn't. I mean, or even inertial, like non-gravitational frames will introduce new relations. Right?
Yes.
So
yes, I agree. Okay, so then what we've got is this duality. What a nice object. This duality between the pure multi-way graph and this all possible foliations thing, where each possible transversal in the multi-way graph is a branchial graph, which can be rolled up into a single node of the branchial multi-way graph.
Right. Right. And my claim is that conversion of one multi-way system to another is the kind of concretization of this functor that takes you from the syntactical category to the semantic one, the categorical semantics.
Okay. So,
and so there's a sense in which this has been studied. There's one area that I'm aware of in which this functorial relationship has been studied quite extensively, and that's in quantum field in functorial and topological quantum field theory. I mean, I don't know if that's worth. Okay, yeah, sure.
Let me just absorb this big idea before we get on to the next one.
Okay.
Okay. So, I mean, the notion here. Let's just try and say the same idea in a bunch of different ways, just to understand it better.
Sure.
So, I mean, the original idea is we've got just a plain multi-way graph, and which could be represented. Let's say it's a string substitution multi-way graph. Okay, and now we're going to make its branchial multi-way graph.
Right.
What is the interpretation of the branchial multi-way graph in terms of the string rewritings? What are the nodes of the branchial multi-way graph in a string rewriting system? Is that obvious?
Well, they're collections of strings that have each node is a family of strings with certain ancestry relationships in the original multi-way system. Right?
Yeah, I understand that point. I mean, it's a branchial graph, but the question is there a different way to say it than just to say, in other words, in the case that you've interpreted in terms of group theory, one can say every node is indexed by a collection of additional relations for the group, right? So, oh, I see. But
it's the same thing. I mean, yes, string rewriting is just monoid theory, right?
Right. So what you're saying is that.
So the original system is like the free monoids generated by the axioms that you gave it, but you can also have restricted. You can also have restricted monoids.
So here's a way to say it. The way to say it is the original graph has all these different. Let's say it's a graph where you're deriving strings from strings and so on, and every node is a theorem. What you're saying is, in the original graph, you've just got theorem to theorem to theorem to theorem. Every node is a theorem. In the other graph, you have bags of theorems. You said it actually, the subset power set construction.
Right.
Every node is an element of the power set of possible theorems from the previous graph.
Right, but it's more general than the power set construction because it's branchial and therefore also encodes ancestry information. That's the sense in which it's a generalization of the NFA DFA conversion.
Let's just go through both of those pieces. Okay, so the first statement is that you have this original graph that has a bunch of, it's essentially theorem to theorem to theorem. And there's a little bit of fuzziness there for me because of this thing about theorems and token event graphs versus theorems as paths, and I don't quite understand that. But let's set that aside for a second. I mean, let's consider that a technical detail now. Okay, so then you're saying the first thing we want to do is, instead of thinking about it as this graph of theorem to theorem to theorem, we say it is a big bag of theorems here that evolve to a big bag of theorems here.
Right.
It's the branchial, but there's additional structure in this bag. It's not just a bag of these theorems. it's a collection of these theorems that are branchially, where we know the branchial relations between those theorems.
Right.
Why does it matter that we know the branchial relations? Is that important for reconstructing this branchial multivariate graph?
So probably, so in the metamathematics case, possibly not. I actually don't know. But one case in which it's very important is in, as I say, the sort of the QFT case.
Okay, well, let's I think we've absorbed. Does anybody have any comments or questions or about this? I understood something. This was at least
things coming up on Zoom if you want to take a look.
Oh, yeah, let's have a look. Okay, it's Dugan's comment, which I saw knows the symbolic sentences. Nick is asking if this dual branchial multivariate graph is the union of path graphs made by all possible foliations with branchial graphs as dual states. I think that's true. I think that's a good summary.
Branchial multivariate graph is a union of path graphs made from all possible foliations.
Right, because each foliation is a path graph, it forms a path graph, and so you just take a union, right? Just like the same way that we do, Monte Carlo sampling.
Correct. That's correct, because that's saying that it's the path graph is the single way system
Yep.
you get by branchial evolution.
By doing the power set construction.
Right. This is a nice object. Okay. All right. Now are we primed to jump into quantum field?
Well, I mean, sorry, I'm not bringing up the QFT thing to be obscure. I'm actually bringing it up because I think it's the area where this is most concretized.
I understand. I'm all for it. I was just pausing for a second, as like a digestion moment. Okay. All right. Let's go into quantum field theory.
Okay, so yeah, as I know, we've discussed quite recently, but maybe to rehash a little bit, there's a sort of, okay, in ordinary quantum mechanics, one has this duality between the Schrodinger and Heisenberg pictures, right? You've got the Schrodinger picture, which is kind of time evolution oriented, and you've got the Heisenberg picture, which is sort of observable oriented. And we know that there's a way, in fact, again, in category theory, there's an explicit functor that encodes the passage from one picture to the other. So there's a general.
Can we just hover on that for a second? Let's think about a quantum circuit.
Yep.
In a quantum circuit, let's walk through what is the Schrodinger picture for a quantum circuit.
Well, the quantum circuits are a Schrodinger picture, right?
So what is the Heisenberg version of the quantum circuit?
The Heisenberg version would be something like, so if you imagine the measurement step at the end of your quantum that actually maps things onto real eigenstates with probabilities. If you imagine that was sort of progressing through time rather than the unitary operators. So ordinarily in a quantum circuit you've got a sequence of unitary operators, these gates, and tensor products of them, and then right at the end you do this Hermitian measurement step. If instead you had a time evolution of those measurement operators rather than of the unitary operators, that would be a kind of Heisenberg analog of a quantum circuit.
So does anybody do that?
Well, for instance, in one-way quantum computing, that's what's done, right?
Because it's Hermitian stuff.
Right. So in one-way quantum computing, what you do is you set up some big maximally entangled resource state, and then you effectively just do local measurements on bits of that state, and then at the end you've got some result. And so it's a sort of, it's a version where your circuit has time evolution of measurement gates rather than of kind of unitary gates.
Let's remind ourselves, just in terms of ordinary quantum mechanics, the Schrodinger picture is kind of you have the wave function, and the wave function is evolving and changing what it is. Mm-hmm. Whereas in the Heisenberg picture, you have an observable operator, like position operator or something, and you are imagining that evolves with time.
Right, exactly.
And so, but in terms of, let me see. So in terms of S matrices, an S matrix, which in quantum mechanics gives you this mapping from the initial states to the final states.
Right.
That is a very Schrodinger picture story.
Absolutely, yes.
Right. So what is the Heisenberg picture analog of the S matrix?
Right. Okay. So, well, there is mathematically, it's what's called a local net of monoids.
Oh boy. Okay. That's why I never heard of these things when I used to do particle physics. They required submerging into the categorical marsh.
Well, actually, I mean, that's a purely algebraic thing, right? I mean, so because mathematically, all that's happening is, basically in the Schrodinger picture, what you care about are linear transformations of vector spaces, and effectively vector spaces and isomorphisms. Whereas in the Heisenberg picture, what you care about are endomorphisms and their isomorphisms. Right?
Endomorphisms of observables to observable. observables somehow.
Yeah, or I mean, the algebra of observables is an algebra of endomorphism. You know, each observable is an endomorphism on your space of states.
Okay, so I want to come back because I understood S matrices years ago as, you know, the basic idea of an S matrix, which shows up all over the place, even in chemistry, chemical reactions, things like that, is you've got an initial state of a system, you know, you've got the state vector of that represents the different possible configurations of the system. You have a giant matrix that tells you what the new state vector is going to be.
Right. So the point I was going to make was that you've got, so all the S matrix is formally is, you know, you've got two vector spaces and you want to ask what's the linear transformation between them, right? Kind of all the S matrix is really encoding. And then, yeah, the analogous thing is you've got two endomorphism algebras and you want to know, how do I map from one to the other? And then there's this, yeah, this local net construction, which I don't claim to understand particularly well, but it's used in algebraic quantum field
Does
theory.
anybody know what the, in S matrix theory, for quantum field theory, does anybody know, because, you know, the S matrix maps a particle, an incoming collection of particles come in from infinity, they interact, they go out to infinity. The S matrix represents the translation between the amplitude of the incoming particles and the amplitude of the outgoing particles. What is the observables analog of that whole thing? Is there a picture of that? I have no idea what the observables must be the correlation functions between the particles. So this must be that must be the sort of mundane particle physicist version of this. Is some kind of statement about correlation functions and some mapping of, okay, so that
That sounds plausible.
right. So I mean, so what it must be is that the correlation functions of the initial correlation functions as well. No, it's not initial and final. It's a mapping between collections of correlation functions.
Right.
Funky. Okay. And what is remind me, the interaction picture is some intermediate version of this.
Right, exactly. So part of the evolution is taken on by effectively the states in your Hilbert space, and part of the evolution is taken on by the endomorphism, by the observables.
Okay, so we've roughly got this picture where, I mean, for me as a mundane particle physicist, it's kind of the, you know, initial state to final state versus correlation functions to correlation, you know, collections of correlation functions to collections of correlation functions.
Right.
Okay.
That sounds reasonable.
Okay, so that's the, you know, Schrodinger versus Heisenberg picture, we think.
Right.
Okay, so now explain you're going to explain algebraic versus functorial quantum field theory.
Right. So functorial field theory is essentially the Schrodinger picture, but in the more general, you know, QFT context. So now you've got some space-time, you've got some manifold, and you can imagine looking at codimension one, slices, effectively space-like hypersurfaces in that manifold.
Or branch-hill graphs, which are you know, branch-hill slices are codimension one.
But crucially, we're in space-time right now, right? So these would be foliations of a causal graph rather than of a multi-way system.
Okay.
At least for now. They will become branch-hill graphs in a moment. But so, all right, so you look at these codimension one slices, and then and then effectively you want to compute an S matrix. You've got these two manifolds, say they're, you know, in 4 dimensions, these would be three-dimensional space-like hypersurfaces. And then you want to connect them along their boundaries. You want to define some cobordism between them, right?
Hold on, let's get the original picture. So we imagine a causal graph that represents the evolution history of the universe. And then we imagine a foliation of that causal graph that represents essentially a space-like hypersurface that has, and you're saying that space-like hypersurface has a three-dimensional manifold that is that space-like hypersurface, and the 3 dimensions in the case of
right.
ordinary 3+1 dimensional space.
Right, and so if you have 2 of those, if you have an initial and final hypersurface, then you could imagine gluing the boundaries together in some way, right?
Which boundaries? What do you mean? These are infinite. Well, okay, these are not necessarily.
They don't have to be infinite.
Okay,
no.
So there's some big blob of space.
Yeah, and if they are infinite, then you know, they inherit the boundary structure of the space-time they're embedded in.
There's a blob of space here. It's the shape of it's some drum that's in some particular shape.
Mm-hmm.
You have another blob of space. It's a drum in another shape.
Right.
Now, which boundaries are you gluing together?
Well, I mean, you're gluing the entire boundary of one to the entire boundary of the other. Right? And that's what the cobordism relationship is.
Yeah, I understand that. Why do you want to do that? I mean,
well, it would be, because ultimately what you want to do is compute an S matrix for, you know, if the first thing is your initial configuration, the last hypersurface is your final configuration, and you want you want to define an S matrix for a process of a given shape. Then
by shape, you mean you're conforming the boundaries of these things.
Right, right. And so the possible shapes of field theoretic processes are given by the possible cobordisms of those manifolds.
So so we've got these manifolds. This is a quantum gravity story. This is not a quantum field theory.
So
this is about
it's both quantum gravity but also more on a more mundane level, just topological quantum field theory, which is kind of.
I mean, you describe this as a causal graph.
Right.
Whereas, I mean, doesn't it have to be a multi-way graph to get to quantum stuff?
Well, yes, we'll see that in a moment. Yes.
Okay, but first of all, we've got one manifold, and we've got another manifold that is from a later slice of the causal graph.
Right.
And you're saying cobordism is this idea of being able to, knit these things together so that their boundaries agree.
Right.
And then you're asking, you're saying there is some, what are you computing about? The interior is somehow one is evolving to the other.
Right, exactly. And you want to know the amplitude associated with that evolution.
Okay, but I don't know how amplitude comes into this yet.
Well, okay, so right, so now if you imagine it as a quantum mechanical thing, so now these are effectively multi-way causal graphs, and so you've got multiple multiple space-like hypersurfaces distributed in branchial space, and you're connecting those boundaries, and you want to know what's the amplitude associated with that collection of evolution paths.
But why are we not doing this purely in the multi-way graph? So we have the multi-way graph, we have a branchial graph here. From the multi-way graph, we have another branchial graph here. We look at the cobordism of the branchial graphs. What does that correspond to? Isn't that an ordinary quantum mechanical amplitude?
Yes. Yes.
Okay.
And in
opposed to a quantum field theoretic amplitude.
Right. Because the whole thing that distinguishes QM from QFT is that you also have to take the causal structure into account with a QM.
AKA you have to take some spatial structure,
right,
to genuinely believe in spatial structure.
Right.
Because the difference, I mean, okay.
Yeah.
Right,
in a sense, somehow, general relativity is the approximation you get when you ignore the multi-way structure and you just look at hypergraph evolution. Quantum mechanics is what you get if you ignore the hypergraph structure and you just look at the multi-way evolution.
Isn't that so beautiful? I mean, that's one of the main kind of punchlines of the whole physics project.
Right. And QFT quantum gravity is some mix of the two.
Right.
QFT being the more structured case.
Right. Right. So, okay, this relates to a question that was asked by one of the summer camp kids about what is the Rullial analog of quantum computing? Let's see if you can get that way. This is the question of if quantum computing is following the different paths of the multi-way graph, what happens if you follow different paths of the Rullial multi-way graph? And what is is there a way of accessing Rullial quantum computing, so to speak?
Yeah, I mean, I don't know. There isn't really at least in my mind, there isn't really a sharp distinction between an ordinary multi-way system and a Rullial multi-way system, right? It all comes down to how you encode the parameter, the original parameter space of your rules.
Yes.
And so, you could imagine, for instance, building a quantum circuit that used, you could have two different circuit, you could have Clifford plus T gates, and you could also have, something that includes that's just stabilizer quantum mechanics with some different gate set or something. And then you could imagine merging those two and building some quantum circuit that combines both. And in some encoding, that's analogous to a Rullial, of a Rullial multi-way system. So I'm not convinced there's that sharp a divide.
Well, but maybe the ultimate divide, which is not unrelated to some of the things you're talking about, is you've got a whole factory of gates. You've got all possible.
You apply all possible unitary transformations.
Right. But the question is that a realizable thing? That is there a way of, I mean, we try with quantum computing, people are making this big effort to kind of constrain what kind of physical processes can happen. Maybe the statement of the Rullial limit is you allow all these physical processes to happen. It's not just these particular ones you're constraining to happen.
Right.
So in a sense, the Rullial, but this is the answer. The Rullial, the Rullial analog of quantum computing is just all possible physics happens, and you must pick your answer out of the all possible things that happened. In other words, unlike...
Well, except that's not quite true, because that's not how it works in ordinary quantum computing.
Well, but in ordinary quantum computing, you have to knit your answer.
Yeah, you have to get things to interfere in a way that. So I mean, ultimately, I think it ends up being an observer theoretic. The final step ends up being an observer theoretic thing. It's not you're selecting the answer from some God's eye picture. It's you actually have to sculpt some reference frame that picks the answer out for you.
Right. All right, let's go back from the Rullial limit of quantum computers, which I think would be, if basically the basic theory of these things is first it goes branchial, then it goes Rullial, and then that's the end. So we think, but then it has to go hyper-Rullial. Yeah.
So is quantum computing speed up real, or is it an illusion?
I'm pretty sure it's an illusion, but I mean, I'm pretty sure that the observer, that the knitting together of things, and maybe even some of the things Jonathan's talking about right now will help clarify that. That the extent to which, when you think about your observables versus Schrodinger picture, the basic idea of quantum computing has to be that in the Schrodinger type picture, a version of what you can say about quantum computing speed up is the Schrodinger picture is enough. The measurement doesn't matter. Whereas there's a different picture that you could take that, that's the question, is that sufficient? Is the Schrodinger piece sufficient? Or does the measurement actually take effort? And I think this duality with these observables might actually tell you something about that. What do you think?
Yes. Yeah. I mean, in effect, Paul's question is a question of branchial cosmology, right? What you're asking is, in a sense, what is the value of omega, but for branchial expansion rather than for spatial expansion? And because that will effectively factor into the question of can branchial space expand rapidly enough that the forward time evolution speed up exceeds the slowdown you get from having to actually apply the observation process.
Yeah, I mean, I think this is like, the claim would be quantum computing is the analog in branchial space of something like perpetual motion. So, the reason that there is in fact perpetual motion in physical space, and it has to do with the expansion of the universe. That is, you can get, and it's, if you have a big wire, a big spring that connects two galaxies that are distant galaxies in the universe, that spring will get more and more tension in it as a result of the expansion of the universe. At least if the spring isn't too big, it doesn't affect the expansion of the universe and so on. But that sense in which you can get energy, right? Energy is not conserved in full cosmology. And I don't, do cosmologists have I haven't really followed the recent stories of energy conservation in cosmology. I mean, it's basically there isn't a Hamiltonian formulation in which energy is truly conserved.
Right. No. No.
Okay. That hasn't changed.
That hasn't changed.
That was how it was 40 years ago.
Well, I mean, resolving that question is equivalent to resolving strong cosmic censorship in some form.
Explain that.
Well, because being able to write down but we don't even know whether there exists a Hamiltonian formulation of GR that's applicable to our universe, right? That's really what the strong cosmic censorship conjecture is. And
why is that? Explain that in terms of remind me, what is the strong cosmic censorship versus weak?
Okay, so the strong and weak cosmic censorship are both statements about effectively whether GR whether you can pose the Einstein field equations as a well-posed initial value problem, essentially as a well-posed system of hyperbolic PDEs. Weak cosmic censorship is a kind of local version of that, which says that you can't that you can't have C1 future inextendable regions of space-time that effectively correspond to naked singularities, right? Strong cosmic censorship is a global version of that statement that effectively says you could define, that the evolution of the universe is, at least relativistically, is determined by some initial Cauchy data defined at at some t equals 0 point.
Okay, so let's just unpack this for a second. So you're saying, in the case of weak cosmic censorship, if we form, let's just talk about it just in terms of black holes. Or space-time singularities, as in the curvature tensor goes to infinity type thing.
Right. But the cosmic censorship conjectures are really statements about hyperbolic analysis, right? So analytically, what's happening is, what does it mean for a hyperbolic system of equations to become ill-posed? Well, it means that your characteristic lines intersect, right? Mm-hmm. And in general relativity, the characteristic lines have a very direct physical interpretation, which is that they are the paths taken by time-like rays. Right, they're the normal vectors to your space-like hypersurfaces.
They're where light goes in space-time.
Right.
I mean, yeah.
Right, and so those your hyper. So and when you think about that geometrically as those light rays being normal vectors to your space-like hypersurfaces, you realize they can only intersect if the space-like hypersurfaces intersect. And so and that's exactly what happens in a singularity, right? So a singularity is a place where characteristic lines converge, and so the field equations become ill-posed there. And the weak cosmic censorship conjecture says, okay, but that's fine because they're cloaked in this those singularity regions are cloaked in this event horizon, which means that although technically your theory becomes there is a region where you can't see one future extend your time-like curves. It's okay because they're sealed off from the rest of the universe. Strong cosmic, so that's really a statement about black holes and event horizons. Strong cosmic censorship conjecture is a statement at the level of the entire universe, whether that happens at a global scale rather than just at a local scale.
Well, but so the strong version does not have the event horizon story?
A strong version doesn't really say anything about black holes, right? It's
whether the singularities, it's like if you have fluid dynamics and you look at the future evolution of the Navier-Stokes equations, do you ever get infinite velocity, infinite density regions of the Navier-Stokes equations?
Or concretely here, it's a consequence of the fact that even though it's one of those necessary but not sufficient things, right? If you have a singularity, it forces your characteristic lines to intersect, but the characteristic lines can intersect without forming a singularity, and that's really the case with this, which the strong censorship conjecture is addressing. And so effectively those conjectures, we know there are spacetimes which they fail, but they're saying, for physically reasonable spacetimes given by some energy conditions, that these things should be true. And so having a well-posed hyperbolic Hamiltonian formulation of GR is predicated in some sense on the cosmic censorship conjecture being true. So we can't even really address the question of energy conservation.
If space-time kind of self-destructs, assessing the total energy of space-time doesn't really mean anything. So then that's the case of the issue is in branchial space, what is the corresponding rate of expansion? And so the claim would have to be in quantum computing, as Jonathan was saying, basically that if the rate of branchial expansion is high enough, then you might be able to get something by basically doing the equivalent of the perpetual motion machine in physical space-time, but in branchial space.
Right, but the thing you brought up, which is this connection to, sort of vector spaces and isomorphisms versus endomorphism algebras and their isomorphisms. I mean, the place where those things connect, to Paul's question, is, in what sense is it that the multi-way evolution graph models, linear transformations, models the Schrodinger picture, and in what sense is it the branchial graphs model endomorphisms and they model the Heisenberg picture? Well, the reason is because ultimately it comes down to something as simple as the evolution edges in the multi-way evolution picture are directed, and in the branchial graph they're not. So in particular, when you reverse everything, which is the analog of a Hermitian adjoint, it's the analog of taking your conjugate transpose. In the multi-way evolution graph, time goes backwards, so that's like unitary evolution. In the branchial graph, it remains the same, so that's the analog of hermiticity. So in effect, it's in that sense we can say the branchial graphs are sort of modeling endomorphism algebras of some kind. And so then in effect, Paul's question is, you've got this apparent speed up that comes from the fact that you can do in the same amount of time, you can do many, many more linear transformations because your branchial graph is expanding. But eventually, you're going to have to apply those you're going to have to apply those endomorphisms. You're going to have to perform those observations that collapse. Anytime you've got a pair of states connected by a branchial edge, you've got to collapse those back to one state eventually. And it's not clear a priori, because it depends on the structure of the multi-way system, whether the slowdown from having to do those observations of collapsing things along branchial edges is going to outweigh the speed up you got from being able to do the things in parallel in the first place. And that's ultimately the question of whether true quantum speed up is possible.
Put in these terms, we should be able to figure this out. I mean, that is, what characteristics, I'm looking at Yorick here because he's thought about multi-way graphs in this kind of way. The question is, under what circumstances does the number of parallel threads outweigh, because what you're asking is, how many, can you have a bunch of parallel threads in the multi-way graph that do not require so much knitting in the branchial graph to get them all back together again? And you might think every time you have a branch in the multi-way graph, that's going to lead to one piece of knitting in the branchial graph that's going to require. So every time you have a pair of parallel edges, that is one piece of knitting that you have to do. Mm-hmm. So the question is, when, is it the case that what you have is just a whole cascade of loose ends which you then have to knit together, and where the amount of knitting you have to do is simply proportional to the number of loose ends.
Right.
If the amount of knitting is proportional to the number of loose ends, then quantum computing is toast.
Yep.
Because that necessarily will just be the same work. You have to do the same work to knit the things together as you would have had to do to just follow each path separately.
So can I rephrase that as the question being whether it is physical to have rules that collapse a large number of parallel threads and introduce a bunch of branchial edges in one single step, because such rules exist, right? The question is if they are physical or if they have physical interpretations. Is that a correct rephrase?
I'd say that it's more like, is the number of rules that you'd need to introduce in order to collapse things down to a single state comparable to the number of evolution edges that you gained by doing the computation in parallel in the first place?
But this question about the number of new rules you have to introduce, this is an observer theory story.
Right, exactly.
That's a question of whether the observer has, we don't yet know how to think about a good meta model of observers. At least I don't yet know that.
Mm-hmm.
And so the question is there a, in that meta model, could you get a boatload of, I don't know. It seems like as soon as you physicalize the observer, you'll never be able to win, because those rules, if you have to enumerate all these separate rules, those all have to be sort of, my intuition is those have to be separately physicalized. My guess is that in the end, it's just going to be exactly the same. That it's just going to be that you can do this quantum computing, and it's one of them is thinking about, in fact, it's exactly the description that Jonathan is giving of this foliations versus vibrations story, because one of them is going to be, the classical evolution is just you follow a single fiber, and the quantum evolution is you're going foliation to foliation, foliation slice to foliation slice. And in the end, a foliation slice doesn't give you an answer. You have to compress the foliation slice. And the story would be, it's just going to take you exactly the same effort to do the measurement as it's going to take you to do the original classical computation.
Right.
My guess.
Right.
And so it's a reformulation. So in a sense, from that point of view, quantum mechanics is a mere reformulation of classical, at the computational level, quantum computing is a mere reformulation of classical computation. That will be the basic statement here.
Right. Or it's another one of those power set constructions, right? In a sense. Classical simulation of quantum computation is,
yes,
essentially what is something like this, right?
Right.
It's the evolving the branchial graphs directly rather than evolving the whole multi-way system.
Yeah, right. So okay, but we stopped you on functorial versus algebraic computation.
I was also going to, seeing as though we're now several tangents deep. I do on the meta modeling of observers thing. So I know we've previously discussed Robin Gandy's PhD thesis and how it kind of missed the point of a lot of. It was
Robin Gandy's PhD thesis because I was trying to figure out what Robin Gandy's handwriting looked like.
Right.
Because I had this random sheet of paper. Okay, this is an irrelevant story, but I wrote about this in some post that I wrote. But a former high school teacher of mine was a friend of Alan Turing's, and somehow when Alan Turing died, this former high school teacher of mine got a bunch of books from Alan Turing. When my former high school teacher died, he gave those books to, various places, but including one was to another former high school teacher of mine with the instructions, give this book to sort of, it may have been basically give this book to me, but it was give this book to, but in any case, so eventually I get this book, which is actually a copy of Dirac's Quantum Mechanics in German, okay? It's slightly obscure because after all, Turing was English, but anyway, he had Dirac's Quantum Mechanics in German. So I'm literally sitting there, this person just handed me this book, and I thought, it's an interesting old book, I should just flip through the pages. So I flipped through the pages, and what should happen, but a piece of paper flutters out. And the piece of paper had on it a bunch of combinators meets lambda calculus, which is pretty weird for a book about quantum mechanics. And so then I went on this little hunt of, who wrote this piece of paper, and that was an adventure. And was it Alan Turing's handwriting? Whose handwriting was it? And I consulted with this person I know who's a forensic handwriting specialist and all sorts of other things. who said, and she immediately said it's not Alan Turing's handwriting, and gave a whole bunch of personality analysis of why it couldn't be. But that's a sort of a different story. But anyway, the end result was eventually this was tracked down to, oh my gosh, what's his name? He died recently. Oh my gosh, the executor of Gandhi's will. So basically, the Gandhi was the executor of Turing's will. Robin Gandhi was the executor of Alan Turing's will, and this person in Wales was the executor of Robin Gandhi's will. Anyway, we tracked all these various people down, and in the end, bottom line was the piece of paper in the book was written by Robin Gandhi, who had somehow had this book for some intermediate period of time. Therefore, this is a very, very shaggy story, but that's why I looked at Robin Gandhi's PhD thesis, was because it had handwritten stuff for Robin Gandhi that was sort of definitively his.
And it's why I spent 2 afternoons grubbing around the Archive Centre of King's College, Cambridge, taking photographs of Richard Bevan Braithwaite's collected correspondence.
Right, which turned out, and then, right, okay, so
and interviewing people at Heifers, as I recall.
Oh yeah, that was another thing. Right, there was also a bookmark in this book. And the bookmark came from Heifers, which is a bookstore in Cambridge. And the bookmark, question was, how old was the bookmark? And the bookmark had a phone number on it. And it was a phone number that, you know, British phone numbers gradually got longer over time, as these things do when, you know, when combinatorially you need that. And so this was a particular length of phone number. Turned out that bookmark had been used for like 40, 50 years or something. They'd been using the same bookmark, which kind of might tell you something about British businesses of that type or something like this. But yeah, and we also tracked down Champernowne, who was another candidate. Champernowne was a friend of Turing's, famous for the Champernowne number, which is the number 0.123456789. 10111213 is a number that has a property that's a normal number. Anyway, Champernowne was also involved in chess machines and things, but later became a well-known economist, it turns out. Anyway, so we tracked down some handwriting samples. I don't know whether you're involved in that part, the handwriting samples of Champernowne, because I've now had multiple pieces of email from people asking me things about Champernowne and handwriting samples. So who knows? It's one gets tangled up in these historical stories. They lead to things like people saying, you know, I am the granddaughter of famous scientist X, and in our attic we have many boxes of interesting notes from, you know, the grandfather or the great grandfather, and I have a great urge to go look at these boxes in many cases, but it takes a bunch of time. Anyway, this is. It was
the only like on the ground detective story I've ever been directly involved in, but
right. It's not as dramatic probably as the Schoenfinkel story, which but anyway, we digress.
Sorry, no.
Robin Gandhi's PhD.
The point I was going to make was that most of Gandhi's PhD thesis is pretty boring. But the second half of it actually has a couple of interesting ideas, and one of the interesting ideas was that he didn't formulate it in these terms, but my reading of what he was trying to do, which is quite interesting, he was essentially trying to construct a formal model analogous to a Turing machine that would take in effectively data and output scientific hypotheses. Right. And so he was trying to construct, he was trying to do it in the language of type theory, which I think was completely sort of inappropriate as a choice of mathematical formalism. But he was really trying to construct what I would now characterize as being a meta model of the observer. And the interesting thing is, because of this known connection between sort of type theory and categorical semantics, I have a suspicion that the meta model of the observer that at least I've been implicitly using in terms of branchial completion has a formulation in terms of Gandhi's original formalism.
So what would you output? So, okay, if the output is, you know, it's just like people say, you know, mathematicians are machines for turning coffee into theorems or something. This is a machine for turning scientific data into hypotheses into scientific laws.
Right.
Which is, I mean, kind of that's the story of statistics. That's the story of the scientific of science in general, is turning of experimental science, experimental science. Shouldn't say natural science, because I think natural science is a little different.
It's also the story of, more abstractly, it's the story of cryptanalysis, right? You're given the outcome, you're just given the output or partial output of some computational system. You're asking what rules generated it.
Yes, but I mean, okay, but so you're saying in that picture, you're saying, did Gandhi make progress on having some, so
No.
how do we parameterize the rules that generate it? So we're saying the system, since we can now represent everything in terms of computation, the output is just a program.
Right.
I see. So the basic point is, it's a code versus data story. And normally the code makes the data, but this is a case where the data is making the code.
Right. Right.
Oh yeah, that's interesting. So that's basically the theory of, so that's a core way to think about observer theory, is that whereas a Turing machine turns code into data, basically, an observer has to turn data into code. Interesting idea.
Right.
Okay.
And it's, I mean, it's one of the reasons why, in a sense, things like combinators are interesting, because they don't have that distinction.
Yeah, the code versus data distinction.
Right.
Right. Well, nor does Wolfram language for that.
That's
matter.
true. That's true. There's a
based on, yeah.
there's a programming language theory for that, a theory term for that, isn't it? It's like unimodular or something. It's not unimodular, but
No, it's well, it's the meta circular,
Just-
but that's
okay.
a different thing. But okay.
I forget
in
the
any case,
terminology.
So what you're saying is, given data emit, what's the formulation in terms of combinators? You would say, given, what is the representation? See, the problem is it's not obvious what the model actually does. And maybe that's related to your kind of models idea and how you knit things together branchially.
right.
Because-
But I mean, for instance, one concretization of that is you're given the causal semantics for a combinator evaluation. Can you reconstruct what the combinator was?
Well, okay, here's a simpler version of that. You're given a collection of combinator expressions. Can you generate a single combinator expression on whose multi-way graph those combinator expressions occur?
Right.
Which is to say that you've got essentially a branchial graph. You can think of that as a branchial graph of combinator expressions, and you're asking, is there a generator that produces that branchial graph?
Right.
Which you could also think of in terms of your branchial to branchial evolution. Is there a branchial graph that generates that branchial graph?
Mhm.
Or you could say, is there an underlying sort of Schrodinger picture, multi-way generator that, multi-way thing that generates that?
Right.
Okay, that's interesting. So back to, what's that?
Yeah, no, sorry. The Robin Gandhi tangent, probably not necessary. We can
No,
go back
that
to.
was very interesting.
Okay.
I mean, code to data, data to code, that's really quite an interesting way to think about things.
Right.
And I think this model of, can you make a combinator which has a specified set of combinators as its branchial thing? I mean, you see, that's a very interesting thing for another reason, which is we've been interested in what does it mean to do multi-computational universality. And so this is an interpretation of that, which is to say, find a computation where on the branchial graph you have certain kinds of things generated. That's very different from the question of, if you're doing an NP computation, right? There's probably a term for that. Maybe there is, maybe there isn't in computational complexity theory. Normally in NP computation, it's like there are many possible branches, and the question is there a winner? Is there a single branch that's the winner? So this is the question of, of all the branches, do you get a certain set if you look across all the branches? Is there a name for that in computational complexity theory? Anybody know? I mean, it's
One that I'm aware of.
because that's I think a different concept.
Although again, I mean, in relation to in terms of the relationship to multi-computational universality, I again have to stress that I have concerns about the syntax semantics distinction, right? Because you're making a statement about what, for instance, what specific combinator expressions were produced on a given branch like hypersurface. But that's not the important thing from a universality point of view, right? It's not important, saying that a system is universal is not equivalent to saying that it generates all, combinator expressions of a particular kind or something. Right. Exactly. What universality is more of, you have to have an encoding of what the combinator expressions mean, and then it has to be the combinator evaluation has to be subjective onto that encoding, but not subjective onto the actual syntax.
Let me give you an outrageous version of this. Question is, can you on the branchial graph reconstruct the time history of an arbitrary Turing machine?
Right.
That's a version. That's a definition of multi-computational universality, right? A bizarre idea. So that's turning a time series into a branchial series, right? So that's saying, normally, and if you go long enough, can you reproduce an arbitrary long time history of the Turing machine in the branchial direction? So what is that like? That's like in, in the ADS CFT world of that correspondence. What on earth is that like? That's like saying, that is in fact.
That's reconstructing light rays from spatial structure or something.
Yeah, something like that.
Yeah.
Right. But that's a good case. Of looking at, can you, that's the thing one could actually do experiments on, is there a branchial correspondence for that, branchial history reconstruction? Right. Are we now ready to pop the stack back to quantum field theory?
Yeah, well, I forget what we were saying now. Yes, all right. I was on the first line of explaining what an FQFT is, right? So you've got this cobordism between these space-like hypersurfaces, and then the point is, when you go multi-way, so to speak, now you associate to the two initial codimension one surfaces, you've now got some space of states, right? You've got some vector space that's the space of quantum states, and in the multi-way system, that's going to be some branch, some collection of state vertices in some branchial graph. And then your cobordism that connects them is some linear transformation, right? And that's the thing that's encoded by your S matrix. The S matrix is concretely the linear transformation that takes you from one vector space to the other.
Yep.
And that's effectively what FQFT is all about. So in functorial quantum field theory, the core ideas go back to the Atiyah-Siegel axioms, the so-called sewing laws that effectively encode the locality of time evolution in terms of functoriality, right? So
wait. Ordinary quantum field theory has a time evolution given by the path integral.
Right.
That is just like what you're saying. It maps one quantum state to another quantum state.
Right.
And those quantum states can be thought of as corresponding to branchial graphs.
Right. And so
ordinary quantum field theory with the path integral just does that.
Right. So in trying to nail down a mathematically precise version of what the path integral is, Michael Atiyah made an initial proposition, which was then slightly refined by Graham Siegel for the case of topological field theories. But the idea was, one principle that your path integrals absolutely satisfy is locality of time evolution. In other words, if you've got a cobordism sigma, and you take the path integral for that cobordism, but that cobordism can be decomposed into a disjoint union of sigma 1 and sigma 2. Then the path integral for sigma should be equal to the sum of the path integrals for sigma 1 and sigma 2.
Sum, not product.
Or well, I'm using sum in that. It would be a direct sum or a semi-direct product or whatever, depending on exactly how you algebraize.
Paths in sigma 1, and they lead into paths in sigma 2, and each one has a I see. If you're doing it in terms of the actual amplitudes in quantum field theory, it would be a product.
Right.
But in terms of the paths, it's the sum of paths.
Right.
Okay. By the way, just for my historical information, that must have post-dated my interaction with Michael Atiyah and my paying attention to quantum field theory. When was that?
Well, the Atiyah-Siegel paper, the one that I'm aware, or the one by Siegel at least, is from 1986, I think, where he formalizes the sewing axioms. That's
a decade after.
Post your high energy phase.
Okay. Okay. So these axioms then have certain properties for these cobordisms.
Right. Well, so the really beautiful thing, and the reason why TQFT got so deeply connected to category theory was this realization that, well, what the sewing axioms really say is equivalent to the statement of functoriality, right? Functoriality is the statement that that your functor, your mapping between categories, respects composition. So f of if big F is your functor and you've got morphisms A and B, f of A compose B is f of A compose f of B. Well, now if your time evolution is a functor, then functoriality is precisely the statement of locality.
Let's go through this. I think I understand this, but
right.
For other people, so in a standard category setup, one of the key aspects of category theory is this compositionality idea that if you have a mapping, A and a morphism A and a morphism B, then you also have a morphism A compose B.
Right. Yeah. So long as they share, domain and codomain in the obvious way.
Right.
Yeah.
and then the idea of a functor is you've got this series of mappings that are these morphisms, and a functor says you might have parallel, sort of in two different categories. You have parallel, chains of morphisms, and the functor takes you from one category to another. And this statement is that the structure of the morphisms in one category are preserved by the functor, in the structure of the morphisms in the other category.
Right, exactly.
Okay, so now let's understand what that means in terms of this statement that the full cobordism path integral sigma is decomposable into sigma 1 and sigma, any decomposition. So sigma 1 and sigma 2 we can think of as morphisms or no, those are functors.
No, so what's really going on is, okay, you've got two categories here, right? There's the category of manifolds and their cobordisms, right? So effectively, the objects are manifolds, the morphisms are cobordisms between those manifolds, and there's also a tensor product. There's also a monoidal structure, which is just disjoint unions of manifolds and cobordisms. So you've got this one symmetric monoidal category which is called board of just n-dimensional cobordisms, and you've got some other symmetric monoidal category, some other category equipped with a tensor product structure, which is the category of vector spaces, right? So each object is a vector space or some Hilbert space in the finite dimensional case. Each morphism is some linear transformation, and there's also a tensor product, which is just the usual tensor product of Hilbert spaces. And then, so in a sense, abstractly, what the quantum field theory is a functor that takes you from one to the other, right? It's the thing that takes the specification in terms of space-time of your process shape and maps it to an S matrix. Right? That's what that functor is encoding, the passage from one to the other.
Well, hold on. So you're saying the S matrix is this mapping, this linear algebra type thing, mapping from this vector space to another vector space.
Right.
And so.
But then you also, on the other side, you've got this picture of of manifolds and cobordisms. And so in a sense, what do you want from a quantum field theory? Well, somehow what you want is some machine that you give me an incoming space like hypersurface, an outgoing space like hypersurface, some process that connects them. And I want to be able to crank some handle and get out an S matrix. And that's what that functor is doing, right? So there's some symmetric monoidal functor from this category of cobordisms to this category of vector spaces.
So another thing to say is, in a sense of quantum field theory, in quantum mechanics, psi, the wave function, gives you, you give it an X, and psi of X returns an amplitude.
Right.
And that's its role. A field operator, a field operator tells you how to think about this. It tells you the whole stack of occupation numbers for any given point. But how do we think about this? What is the field operator? What's the because this is what you're talking about is your vector space thing, the instantaneous moments inside the operation of the S matrix,
right, are
a series of states of the field operator.
Right.
But how do we think about the field operator? Gosh, it's a long time since I thought about this. The field operator takes, the whole point of a quantum field, in quantum mechanics, you just have one amplitude, and it is the amplitude in an electron. What is the amplitude that the electron is this position or that position? In quantum field theory, it's a stack of things in the Fock space where you're saying there can be one electron, two electrons, three electrons, etc. And at each point in space, the field operator tells you what the essentially amplitudes of every possible number of particles at that point are. Mm-hmm. So this now is asking you. So that's the microscopic version of the S matrix at every moment in time. Right. So how does that?
So it's important to note. So far, everything I've said is just quantum mechanical. We'll make it field theoretic in a moment, right? Okay. This locality of time, the locality of time evolution that you want from your path integral is now just a statement that this functor is a functor, right? When you take disjoint unions of manifolds and cobordisms, they map to essentially just matrix products in the category of vector spaces and linear transformation.
There's a functorial correspondence between the sort of the partial. A little piece of cobordism evolution, so to speak,
right?
A little piece of vector space evolution,
right? And so you can split it. You can split them up, however as much as you like, right? That's what the locality is saying.
That you could say, the steps in this cobordism evolution one step and then multiplied by another step. And that's like two pieces of an S matrix. The initial S matrix, the final, the initial S1 and S2.
And then you just take a matrix product. And
Right.
you get, yeah,
and
exactly.
Which is the same as the sigma 1, sigma 2 successor relation.
Right, right. But the important point here, though, is that in constructing that, we've already assumed effectively a default time slicing, right? We've assumed a gauge choice in how we've broken up the cobordism, between these two hypersystems.
Whereas we don't even know how that works in the S matrices, because in the S matrices, if we thought about that in terms of Feynman diagrams, we'd be having a bunch of particle lines, and then we'd be deciding in this. In fact, it's kind of amusing that the Feynman diagram is itself a graph, and you could imagine essentially foliating the Feynman diagram graph, just as you can imagine foliating this other thing.
Well, not to seem like too much of like a category salesman, but that's actually not so much of a coincidence when you appreciate the compositional structure of what's happening. A Feynman diagram is a string diagram for the symmetric monoidal category of vector spaces and their isomorphisms, right?
Oh, okay.
Which kind of makes sense when you think about it. Right. Okay, but yeah, so and obviously we don't know how to do this in general, because in a sense, if we knew how to do this in general, we'd have solved quantum gravity. But we know that, in order to get quantum field theory, you at least have to consider you have to mod out by gauge choices in some sense, right? And so this is why in a sense, quantum mechanics is like the one category case where you've already assigned, you predestined your time slicing. But then you could imagine having higher morphisms. You could imagine having, if you imagine several different possible time slicings in your cobordism category, and then gauge transformations being higher morphisms between them, then you get some n category of cobordisms and some n category of vector spaces, and that's so in a sense, this is one of the reasons why I think this is such a mathematically beautiful formulation, because in a sense, quantum mechanics is the one category case, quantum field theory is the n category case, and then the hope would be that quantum gravity is some infinity category case, right?
Right. Well, let's go through that, Clay. So you're basically saying quantum mechanics has a specific time evolution independent of spatial gauge choices. Basically.
Right.
And what you're saying is, although I claim there is another kind of gauge choice, which is this branchial gauge choice, which we'll come to in a minute. Maybe.
No, but right. Well, precisely. But that functor, the functor between those two higher categories, is the thing that maps you from a from a space-time gauge choice to a branchial gauge choice.
I see. That's your claim. Okay. All right.
Yeah,
Okay. So
that's my claim.
Okay. So let's walk through that. So what you're saying is, I say it's kind of nice. Right. Okay. So on the one side we have a bunch of these cobordisms between these different layers in this causal graph type thing.
Right.
And then we've got either one foliation, which means one codimension one sequence of these space-like hypersurfaces. That corresponds to a particular evolution, and that's it sounds classical, but it's actually a particular quantum evolution. Right. Okay. So another possibility is that we pick different choices for that foliation. We can pick an infinite number of different choices of that foliation. The mapping between foliations is a gauge choice mapping, and that's making gauge changes, and those correspond to a different kind of I guess, what is that? Is that another functor? Is that
that's a higher morphism. Right?
Yeah, okay, it's a higher morphism, so it's a morphism between morphisms.
So
the first.
Yeah, so in the multi-way picture, right, you could imagine you've got some multi-way system, each path is a different gauge choice. But you could also imagine, rather than just like sort of somehow imposing from the outside that, you hop from this path to the other to make a gauge choice, you could imagine having an explicit rule that lets you map from one path to another. And those are effectively higher morphisms.
So in mathematics, those are proof-to-proof transformations.
Right.
Which is something that you were working on, but I think more work needs to be done on.
Yeah, no, absolutely. But I mean, so for the case of multi-way systems, the work that, well, particularly Xerxes has done, but also myself and Hatem have kind of helped out a little bit with, is, essentially looking at that question. How do you define higher morphisms, higher homotopes, and so on in kind of arbitrary multi-way systems? And so in the field theory case, those higher morphisms have a pretty tangible interpretation as essentially gauge choices, right?
Right. So just
or gauge transformations, sorry.
People's benefit in case people were not. Proof-to-proof transformations is things like you have one proof, can you find a simpler proof? Can you simplify that proof? Which is a concept, a sort of higher level symbolic math, symbolic computation concept, rather than just, can you simplify this algebraic answer? Can you simplify the proof that led to this algebraic answer? Anyway, so we've got, on the one hand, we've got these higher morphisms, and you say that we are mapping those higher morphisms to higher morphisms on the S matrix side, which correspond to different cuts in the oh boy, this is there used to be these things. This is funny. There's these things called these Kutkowski rules, I think.
Okay.
Which are in fact probably the same as cuts in the in proof theory, which is just really ironic, given that one of them is just named after a person. And okay, in any case, so the idea is you've got a Feynman diagram that represents all of these different possible, and when you can say, I've got the beginning of my S matrix is one part of the Feynman diagram, I've got the end of the S matrix, another part of the Feynman diagram, and I can make an arbitrary slice between those two. I've got a bunch of loose electrons and photons and things going through, and I can decide to make that cut after the electron and positron annihilate or before, and those are different possible choices of essentially sort of, well, what the heck are those called? In Feynman diagrams, those are the that kind of factoring. Boy, that was studied in QCD back in the day. Yeah, okay, I mean, it's clear what that means. You have a Feynman diagram and you can slice it at some point, and then as you knit those things together, you have a bunch of complicated integrals to do to actually evaluate the Feynman diagram.
Right.
But it's clear you can conceptually sort of slice it in that way.
Mm-hmm.
Okay, so what? So now what happens?
Right. I mean, yeah. And so as I say, if you restrict only effectively to the gauge choices that correspond to Lorentz boosts, then you get some you get some restricted kind of N category, and that models quantum field theory. At least that would be the claim. But then if you include
you're saying on the if you restrict the gauge choices that you're making on the cobordism thing to only what? Lorentz transformations, you're saying?
Or Poincare transformation,
All right,
yeah.
As opposed to general relativistic general diffeomorphism.
Right, exactly. So effectively, you've got one class of higher morphisms that's just modding out by the Poincare group or some connected component of the Poincare group, and you've got another that's modding out by the full conformal group or the full diffeomorphism group of spacetime. So QFT corresponds to the former case, which is a restriction of the latter, and the claim would be that full quantum gravity would correspond to the latter case.
Okay, but in the case where you just described, where you just have Lorentz transformations, you're saying you just sold me this thing about Feynman diagrams, or I sold myself a thing about Feynman diagrams, and but in that case, the slicing of the Feynman diagrams, in the case of general diffeomorphism, what? Oh, I see.
It's just you can stretch it topologically. Any topological transformation of the Feynman diagram is permitted, whereas the ordinary transformation is you are only allowed to
I
effectively.
don't think it's that. I think it's more complicated than that, because I think the particle states change. In other words, what happens when you go into non-trivial space-time is this notion of particle states, which was just the electron with the electron propagator. The electron propagator changes because you're redefining the particle states. You're redefining, even in an accelerated frame, you're redefining the particle states.
Right.
So how does that? I mean, there isn't really a good generalization that I'm aware of. I mean, you can do. I mean, like the original Hawking effect is associated with doing Feynman diagrams, basically very simple Feynman diagrams where the propagators are in a curved spacetime.
Right. But I mean, QFT in curved spacetime is pretty well solved, except for the back reaction, right?
Which is otherwise known as the effect of gravity on everything, which is otherwise known as the main story of quantum gravity.
Right. Well, yeah, of course. I mean, this, yeah.
Right. But so what you're saying is, I see. So maybe the point is that you're saying that there also have to be graviton lines in the Feynman diagrams, and then the traditional stuff all goes to hell because I mean the back reaction in a Feynman diagram, back reaction has to be represented by the effects of gravity on other particles, which is otherwise known as graviton.
Right.
Graviton lines. Okay, but so all right. So we've understood a little bit about the correspondence. You were going to make some other point about this correspondence between I mean, this Actually, I have a question about the correspondence to quantum field, to ordinary quantum field theory from this multi-way graph thing. So one important question, one important practical question is, can we find a better way to do numerical quantum field theory? Because numerical quantum field theory, the only way that's known right now is lattice gauge theory. Lattice gauge theory requires this Wick rotation to Euclidean space. It's a big mess.
Right.
And so the question is, with this correspondence between the multi-way graph on the one hand and Feynman diagrams, S matrices on the other hand, one might think that one could use that to use the pure multi-way graph as a way to do, computations in quantum field theory. Do we know if that works?
I don't think we know if that works. I mean, one way that you could do, certainly one way you could do relativistic quantum mechanics, which takes you most of the way there, would be, so if you've got a multi-way evolution graph, right, that's the kind of model of a monoidal one category. If you then add in the causal edges, so you get a multi-way causal graph, evolution causal graph, I should say, that's effectively a weak form of two category. And in a sense, so relativistic, so whereas we know how to, pretty much know how to do ordinary quantum mechanics over the one category, over the multi-way system. If we could do an analogous thing for that weak two category for multi-way evolution causal graphs, that would presumably correspond to relativistic quantum mechanics.
How would we see that? So I mean, let's say, how would we get like the Dirac equation out of that? I mean, how would we see the difference between getting the Schrodinger equation and getting the Dirac equation?
Well, so we know, okay, as we discussed the other day, there's a sort of standard way you can get something like the Klein-Gordon equation in a causal graph, right, or in a multi-way causal graph.
Well, so you were saying by putting weights on the causal graph.
Yes, but we're also, I mean, that's one way you can get it. You can also, I mean, yeah, that's essentially, that's one of the approaches that's developed in causal set theory, right? Because you define it, you define a D'Alembert operator by essentially equipping the causal set with a bunch of, every element is associated with some scalar value, and then you just sum over causal layers. But you can also think of the causal graph as intrinsically defining a differential operator.
Okay, so just for people's benefit, I mean, so the issue is, normally a causal graph is just a thing with nodes, but you can always put values on those nodes, and then the thing becomes more like a partial differential, more like we should call it a finite graph as opposed to finite elements, a finite graph approximation to a partial differential equation. That's a good term, actually. So in that finite graph approximation, one would eventually, the point Jonathan is making is that there's a limit in which that finite graph approximation limits to the Klein-Gordon equation, to the massive or massless? Massive.
I believe the massless is I may be wrong on this. I believe the massless case is the only one where it's known. There is an ansatz for the massive form. I don't know if that's been proven to be correct.
Okay, but I mean, in a sense, this is going to be obvious because this is essentially a form of the wave equation.
Right.
Which is, and it works on the causal graph because the characteristic lines of the wave equation are just this crisscross thing, I think. Right.
Anyway, so what one would expect, I assume, is if you did the associated thing on the multi-way evolution causal graph, so now you've got two classes of edges, you've got causal and evolution, then some mixture of the Schrodinger operator and the Klein-Gordon operator would give you a Dirac operator on this structure.
Of course, with the Dirac operator, we need spin a half, which we don't yet understand.
Right.
Et cetera. But that might be some square root of some. I mean, that would be very nice. In fact, that's a good point. That just as if it is true, if it is true that the Klein-Gordon operator comes by having these sort of crisscrossing these diamonds.
Yes.
In the multi-way graph.
Right. Then commutation of your field operators that gives you spin zero, for instance, is essentially merging of branch pairs in the multi-way system.
The Dirac operator, which is the square root of that, would naturally be a single branch.
Right.
Which is what we guessed ages ago.
Just heuristically,
the correspondence between fermions and bosons. So that would be that's actually worth working out.
Yeah.
Whether because that would mean that in a very literal sense, the Dirac, fermions are the square root of bosons because they're the things that come from single branches in the multi-way graph.
Right.
Okay. So how many more things can we solve here? That's a good piece. So okay, but let's see. You were I think you still had to explain this functorial quantum field theory, which you had explained as being this notion of this cobordism evolution.
Right, right.
And then you were going to explain maybe also algebraic quantum field theory.
Right. So the point is that in addition to associating a space of states, you could also to each hypersurface, you could also associate an endomorphism algebra, right? You can also associate some algebra of observables. Right. And
well, it's not so obvious how that actually works to me. I mean, that is, you've got this, so the algebra of observables, as I was sort of yakking before about correlation functions, I don't really understand. Given a graph, I mean, the algebra of, I don't see this. Because I mean, the unitary evolution, I clearly understand. It's just you follow the edges, you go from this to this to this.
right, right.
In the case of observables, is the algebra of observables, is it something as simple as you're looking at the relationship of edges in the branchial graph or something? To
Right. Well, exactly. I mean, so okay.
Which are exactly correlation functions. Edges in the branchial graph are exactly correlation.
Right. And the reason they correspond to endomorphisms is because they're the things along which you can complete. Right. So if you want to perform observations, those are the observations you are able to perform.
I think that's right. But notably, the point is, and I was wondering about this. I mean, there's this in statistical mechanics, there's these cluster expansions and things. And I wondered this because I wondered this in connection with Matt's project about from whenever it was
2020.
Yeah, right. About hard sphere gases, because I wondered whether there was what the interpretation of the branchial graph, and I guessed that the interpretation of the branchial graph is one of these cluster expansions. That's sounding more convincing. Okay, so anyway, so what you're saying is the branchial graph maybe the branchial graph represents the collection of correlation functions. It's essentially an encoding, just like it's an entanglement map. It's also a correlation function map.
Right.
And okay, so then.
So yeah, because in effect each state is some eigenstate, right? And then
Yes.
and then every branchial edge, one way you can think about it is it's one possible projection that you can perform of an eigenstate onto another.
Yeah, which is otherwise known as essentially a correlation.
Right. No, I'm agreeing. It's
Yeah, that's nice. Okay. All right. So anyway, so we've got this endomorphism, whatever the endomorphism, collection of endomorphisms between operators.
right.
Okay. So which is otherwise known as a branchial graph. Okay.
Right. And so the original Weitmann axioms for axiomatic quantum field theory and the more modern kind of I say more modern, not particularly modern, but the slightly more refined version of the Haag-Kessler axioms for algebraic QFT, those are effectively describing the same field theory, but at the level of the endomorphism algebras and their isomorphisms, rather than at the level of the vector spaces of states and their linear transformations.
Right.
And so the statement that these two pictures are dual, that Schrodinger and Heisenberg are dual, is stating that effectively the multi-way evolution graph and the sequence of branchial graphs are encoding the same multi-way evolution.
Right. So
And that one can be reconstructed from the other.
FQFT and AQFT.
Right.
By the way, in AQFT, just a modernity question, does the A stand for axiomatic or algebraic?
Algebraic, because both are axiomatic, right? Both FQFT and AQFT are axiomatic field theories. So they're just two perspectives on it.
But the Haag axioms were not stated in terms of observables originally.
No.
They were stated in terms of asymptotic states and field operators and things.
Right. The Haag-Kessler formulation is a modern refinement. Although, as we discussed the other day, there is a pretty direct way of obtaining the statements about asymptotic states from those axioms, from the modern formulation.
Branchial surface evolution versus path evolution duality. I guess we are considering equivalence classes of multi-way systems up to renaming the single states, right? Because the only way we can say they are describing the same process is structurally, right?
Right.
Yes.
Right.
Yes.
That's true.
Yes. But so what's the conclusion of this? The conclusion is that there's this nice correspondence between branchial evolution and temporal evolution, basically.
Right. And so, I mean, one of the exciting things is that so, as I say, the reason I got interested in this was actually not so much because I was interested in field theory, although that's obviously interesting in its own right, but more because this seemed to be the case of this, I think what we can now reasonably think of as this functorial transformation between multi-way fibrations and multi-way foliations, this was the case where that functorial relationship seemed to have been explored to the greatest depth. Because, for instance, in some of the work of Urs Schreiber and the other people who are doing kind of higher gauge theory stuff, there is a very concrete construction of this functor that takes you from endomorphism algebras and their isomorphisms to vector spaces and their isomorphisms.
So, okay, just we should probably wrap soon. I could go on this for ages and ages. But I mean, let's just zoom out for a minute. Okay, so we've got this categorical, this correspondence between, I mean, this is, what's interesting about this is the same story. It's ADS-CFT, it's the same thing as, you know, AQFT versus FQFT, it's the same thing as Heisenberg versus Schrodinger. This is just some sort of fundamental duality that exists across lots of kinds of systems.
Right.
So what else can we figure out from that? And it's also the thing between model theory and proof theory, I think.
Right. I think so.
And that these are all equivalent dualities. So what other dualities might there be like that?
Well, I mean, this is actually something I wanted to ask you about because, in a sense, so I think both of us, for various reasons, are getting interested in this question of, you know, how can these multi-way, you know, how can the formalism of multi-computation, for instance, be applied to chemical reaction networks or, you know, ecological systems in biology and so on. And in those situations, I think a lot of those correspondence, I mean, presumably if multi-way systems are a good model, then those dualities should also exist. But I don't think we know their interpretation in those kinds of areas.
Right. I think the branch hill graph, I mean, the story in chemistry, for example, the story of the branch hill graph.
It's just what ambient chemicals are around at a particular moment of time, right? That's the...
Yeah, I mean, the story of causal graphs is the thing which is less clear in chemistry. I mean, chemistry people don't talk so much about causal graphs. They talk merely about what chemical, you know, they talk about chemicals making chemicals. They don't talk about the causation of one reaction having an effect on another reaction.
Right. Although, I mean, again, as I think I mentioned the other day, it's like, so like in a very minimal case of this, you could just say, so, you know, imagine you have a multi-way system that is just encoding stoichiometry, right? So you just know populations of certain chemical species, but you don't know anything. There's no other kind of reactivity rules encoded. And they're just interacting in ways that are sort of algebraically permitted. Well, if you start from the assumption that everything's at a kind of uniform pressure and temperature and so on, then in a sense, the causal structure of that stoichiometric multi-way system is telling you about the energies of particular chemical species, right? How many previous times have these things interacted? You know, how many times has this thing bounced off that thing? How many times have these things interacted? And so then you can start to develop a pretty minimal model of something like activation kinetics, just in terms of causal structure. That's a place where I think even in conventional chemistry there is.
Well,
you know,
I mean, because at every reaction there's a change of energy. And you're saying the causal graph is measuring the change of.
You can do energy bookkeeping using causal structure, even in a multi-way system where there's no information about that baked in.
It's sort of a shame though that in the world of correspondences that or maybe it isn't. Maybe, gosh, that would be terrible if it was correspondence. But that the density of causal edges, which in physics corresponds to energy density, is also energy density in chemistry.
Right, but at a completely different scale.
Yes, a completely different scale. It sounds like in this interpretation, that is what's being said.
Well, I mean, so, and actually, I'm going to necessarily be a bit more speculative because these are areas I don't really know anything about. But so, you know, one thing I've become interested in recently is, so for instance, when you're modeling either chemical reaction networks or biological systems as multi-way systems, you know, that there is a very multi-way-like approach that's already been adopted in kind of mathematical formalizations of these things, which is Petri nets. And as we know, Petri nets are effectively token event graph, or I would argue more precisely, they're global multi-way systems in which the token, you know, the Petri net tokens are tokens and the transition firings are event firings in some global multi-way system.
Although Petri nets have deduplicated all. I mean, a minimal, an ordinary Petri net deduplicates the tokens.
Right, but not in, for instance, the colored case that Paul is interested in. Or I mean, there are things like whole grain Petri nets and sigma nets and so on, which have slightly more sophisticated semantics.
I've wondered for years what a sigma net is.
I'm not sure I can reasonably explain it. It's
I'll still keep wondering what it is. Eventually it might show up.
Or at least not in a reasonable time frame. But no, I mean, they're effectively like Petri nets, but with a different deduplication semantics and a different execution semantics. That's the basic idea. But the point I was making was, okay, so in kind of if you take something like either chemical reactions or ecology, it's pretty standard in very minimal mathematical models to use essentially a kind of mass activation law, right? That's effectively what things like the Lotka-Volterra equations do. That's what that's what the exponential growth model does, etc. But we know that that's a bad model for things like macromolecules in chemistry and for things like enzymes. We also know it's a bad model for population species because, for instance, in predator-prey models, you get predator satiation and that kind of stuff. And so,
Wait. You're saying, I mean, Petri nets were originally invented by, Carl Adam Petri when he was a high school kid as a way of modeling chemical reactions. I'm
not even sure, was he younger than that? It was 13 or 8 or it was some ridiculously early age. Was he in high school by that point?
I don't know.
I think it might have been middle school.
Maybe middle school. I don't know. Depends on where the German divisions between, I don't know whether they have.
It's very, I mean, it must be strange to have really the only thing that you're known for. He has some long distinguished academic career, and the only thing he's really known for is this thing he invented when he was like 13.
It turns out, I was reading, he has an autobiography. And it turns out I had thought that, and also I exchanged some letters with him actually, which were quite odd. But, and so I was really kind of confused about what his whole story was. But the fact is that this thing he invented early, he went through, and as computer systems became important, he kind of applied Petri nets to computer systems, and that became the whole story.
Right.
The chemistry application of Petri nets kind of fell away very quickly.
Right.
But now the chemistry application is back because the Petri net, says you have these tokens, they accumulate, so to speak, and then you can have a firing, a thing that happens, an event that happens that is like you have to have, I know nothing about chemistry. You have to have 2 hydrogens and an oxygen or something, and then you can make water.
Right.
But you need both of those tokens, all of those tokens to have the event of making water, so to speak.
Right. Anyway, so the point I was making, so there's a pretty standard approach to setting up that formalism in chemistry where you essentially say, we've got some set of chemical species, you've got some function that maps that set of species to the natural numbers that tells you essentially like how many of such and such a molecule is there. You construct some directed graph where every vertex is labeled by by a function by what's called the chemical complex, which is that function, and then there's a direct way of mapping those graphs onto Petri nets and back again, but. The point I was making was, ordinarily rate laws are not encoded in Petri nets, right? That's something you have to, that's something you have to encode subsequently.
Yeah.
You have to place some kind of weighting on each edge. And similarly, I mean, that's kind of true with the multi-way system, right? You can use the kind of trivial, when you construct a multi-way semantics for these Petri nets, you can use the kind of trivial path weighting, but you could also imagine having a multi-way system where there's a different kind of function that tells you about what the path weights should be. That's really the same as what's going on with rate laws. The point I was making though is that, in traditional mathematical models, we've used pretty terrible rate laws, things like Lotka-Volterra use essentially these mass laws that assume that,
if there are foxes, then they can be eaten by.
Right. Which is kind of assuming that biological species act like idealized gas molecules or something. Where there's but what you want is for instance, is it called the I should remember this name. It's like the Michaelis-Merton model. There's some trivial modification you can make to the mass law that's used that's like the most popular model of enzyme kinetics. That's like a kind of satiation version of that, which can also be applied to population dynamics to model predator satiation.
I heard of that law. What it says.
Oh no, I mean it's just a mass activation law, but with like a denominator that kind of induces a decay effectively. Mm-hmm. Anyway, so the point I'm making though is that my suspicion, which I have some technical. I have some formal evidence for, but it would be nice to get more, is that in general, those different activation models effectively correspond to different functions that you can apply to the causal structure of the associated local multi-way system. So for instance, statements about thermodynamic equilibrium in chemistry, I suspect effectively correspond to statements about causal cyclicity in the, when you equip the local multi-way system with some causal semantics. If it becomes possible, thermodynamic equilibrium is equivalent to the statement that there's, that your chemical reaction can kind of go in both directions with equal, with some kind of.
Well, let's see. So
And then,
go ahead.
and then yes, and then so things like the activation kinetics that I was talking about earlier in relation to like a stoichiometric multi-way system, that would be again a very simple kind of use of the causal structure where you're just using causal edges to essentially bookkeep information about energy. But one could imagine defining kind of arbitrarily sophisticated functions over the causal structure that would correspond to presumably different kind of activation models, different energetics models.
Well, I mean, look, in general, the plain multi-way graph, I mean, it's kind of reminiscent of, the sort of capacity in information theory versus Shannon information and so on. It's the unweighted, it's the what can happen versus with what weighted happens.
Right.
And in our traditional multi-way graphs, there is no weighting except path weighting.
Right.
And so what you're saying is,
you could, in effect, very concretely, what I'm trying to say is that you could imagine in the multi-way system specification there being another kind of function that selects path weights based on information about the causal history of that path.
yes. Well, let's think about that for a second. So, I mean, the most naive thing is you've got a node in the multi-way graph and it has certain path weights coming into it.
Mm-hmm.
And you could imagine one thing you could do is you could take the outgoing path weight as some function of the incoming path weights, just at the pure multi-way level,
Mm-hmm.
forgetting anything about causal stuff.
Yeah.
And then you could equally well have in the causal graph, you could also have this kind of weighting theory where a particular event, if it is caused by a couple of other events, has some weighting, some path weighting of its outgoing edge that is some function of the path weights of the incoming edges.
Right, right.
But
And so the point I'm making in relation to those different models of kind of rate laws, and like the Michaelis Merton model, is if you want to model something like predator satiation, then
what are you talking? What is that word?
What?
Satiation. Oh, satiation.
Satiation.
Full. It doesn't
Sorry,
even chocolate.
You're one of the few people I expect to be able to understand my accent. Why are we having this communication problem?
It's been too long.
Satiation. But no, so if you just have the pure multi-way structure, it's hard to encode that. Whereas what you want to be able to do is say effectively, if this lion has eaten 20 gazelles in the last day, it probably doesn't want to eat another gazelle, and that's really a statement about causal history. And so, so my abstract statement is that these different activation models are just different functions you can apply to the causal history of paths.
Right, right. But I mean, I'm not sure that saturation idea is not. I'm not sure that's the most important idea, but maybe it is.
No, it's one example of where, because in effect, if you just have a multi-way system that's doing something like ordinary Petri net semantics, just transitions fire when they can fire, that's just like the mass law, right? Yeah. And so I'm saying if you want to have more realistic rate laws, Mads, who is an actual chemist, has a.
My question, you mentioned some functions connecting some species with some other species. Is it like a function that tells you start with some chemical and will end up with some other chemicals? Can you clarify more? What do you mean by those functions? What are those functions?
Right. Okay. So we've got two different levels of stuff going on here, right? So in terms of just the ordinary multi-way semantics or the ordinary Petri net semantics, yeah, exactly. So you've got. I mean, it's going back to like the statement about axioms and free structures, right? In a sense, the free algebraic structure of chemistry is stoichiometry, right? Where things have to balance. And so in that case, every token in your global multi-way system or in your Petri net is labeled with some chemical species. And then there are just simple rules that are imposed axiomatically that say that transitions can fire as long as they preserve the numbers of those chemical species. You can then define a more sophisticated function that restricts that more based on, exactly as you say, some statement of the form, these things can come in, these things can go out. But this class of chemical reaction is not permitted for some other reason. Then the point that I'm making is, well, you can have situations where, chemical reactions are the transitions can fire only in certain situations, where those situations are not just a question of, do we have the requisite tokens, but for instance, do we have the right temperature? Do we have the right energy conditions? And my speculative claim is that in general, those activation conditions can be encoded as questions, essentially queries of the causal history of those tokens, right? If you can know how many other tokens has that token interacted with, how many other things has it bounced off, what is its complete causal ancestry, then my conjecture would be that gives you all the information you need to be able to encode kind of arbitrary activation conditions.
Sorry, more than enough. I mean, in other words, the actual models will not need to know the complete history of all meals the lion has eaten.
Right, right. It would be some coarse-grained thing.
Right.
John, yes, right.
So just to rephrase that last point that you made, you're saying that the sort of coarse-grained thermodynamic variables can be read off as the causal history of the individual events. Is that the claim?
I think that's the idea. I mean, and we see that in, for instance, as you say, in Matt's projects, right? Where you can infer essentially temperature. When you've got causal graphs generated by hard sphere gas collisions, you can read off things like temperature just from causal structure. And if that's a more general principle, which I think we believe it is, then
right.
Then
So then we have to figure out what's the analog of boosts and reference frames and event horizons and so on. We know some of those things for chemistry.
Mhm.
Yeah.
You know, coarse graining, like a very basic topic is statistical mechanics. Like, you know, I don't think there's any consensus on what is the true definition, like, you know, when that transition happens.
We are talking about coarse graining in a much more abstracted, the level.
Technically, what do you mean by coarse graining?
It's a general concept. I mean, coarse graining in statistical mechanics is part of this observer theory story. That is, you know, the molecules bounce around as the molecules bounce around, but we observe only certain aspects of what's happening with these molecules. One of the key observations back from MKS times is that the reason the second law of thermodynamics works is because the only coarse grainings we can do are computationally bounded coarse grainings. And the underlying system is generating computationally irreducible behavior. And that's why we believe in the second law of thermodynamics. So, by the way, I mean, in terms of history of statistical mechanics, the history of statistical mechanics is, you know, Boltzmann originally had this idea of, you know, entropy and all this kind of stuff. But then there's this kind of bug that you really have to do coarse-grained entropy. Otherwise, it's always entropy zero because it's just a unique state. And the question is, what's a valid coarse graining? You know, Gibbs in the 1920s, 1930s kind of clarified this notion of coarse graining, but not how you would do coarse graining. And so I think the thing that I understood in the 1990s was this fact that, you know, you can think about coarse graining as a computational process. And when you think about that, you actually can nail down what is a valid coarse graining. Nobody had been able to do that before. This idea of what is a valid coarse graining in the books of, you know, my favorite is a book about statistical physics, which proves Boltzmann's H theorem, the theorem that entropy increases with time, which is based on a statistical argument about molecular collisions. And it says at the end of the section, it says, you know, it proves that H decreases, entropy increases with time. And it says, but you can run this whole derivation in reverse, which means that entropy would decrease with time. The last sentence is, this point is often puzzling to the student. And it's been puzzling to everybody. It was puzzling to everybody from Boltzmann on. I think that that's finally resolved by thinking about this computational boundedness observer story. And it's, I mean, and by the way, the reason you can do those proofs both ways around, it's just a statistical mechanics fact, is that in the proof, you assume that molecules are uncorrelated before they collide. But the fact that they're uncorrelated before they collide, once they've collided, necessarily they're correlated because they just had a collision. And that's probably not unrelated to things that we have to think about for chemistry.
Right.
I mean, you know, some of this is not figured out. And by the way, when we talk about, you know, entropy and entanglement entropy and all these kinds of things, it's all, you know, there are all kinds of issues that come up about what kind of coarse graining you're dealing with. What, you know, when you talk about entanglement entropy, it's like what is the set of things that you are constraining to say that you're talking about, and then how many states are consistent with that?
I mean, so in the context of multi-computation, or at least in the stuff that I'm talking about in relation to global multi-way systems, coarse graining has a very precise meaning, which is just that it's the state equivalence function that you use, right? So, you know, in ordinary multi-way systems, you could, if you're doing graph rewriting, you could imagine treating every pair of graphs where same Q returns false as being distinct. But for most cases where you want to do graph rewriting, that's not particularly useful. You want to merge based on a coarser criterion, which is graph isomorphism, right? And so your state equivalence function is not same Q, it's isomorphic graph Q. And so those are two rather trivial examples of kind of essentially coarse graining functions. And yeah, the point with observer theory is that one's defining a much stricter and therefore much coarser potential class of coarse grainings, right? Because, you know, We don't expect physically realistic observers to be able to do actual isomorphism distinction. They're distinguishing something that's much coarser, that's more like at the level of thermodynamic variables.
Right.
I have a question and one comment. Like, question is, why did this book say that reversing the process would decrease the entropy? Because we know, for example, from partial differential equations, like or even the heat equation, that time reversal is not equivalent to entropy.
The heat equation is at a higher level. The heat equation, yeah, the heat equation is a parabolic equation that is at a higher level of description. I mean, this is at the level of molecular dynamics, where every molecular collision is reversible. Right? And so what the H theorem is doing is it's trying to say, based on just looking at a collection of reversible collisions, what is the conclusion for the entropy as measured in terms of the number of states consistent with the system? And that's the, so by the time you're at the heat equation, you've already assumed the answer.
I see. But even in the state of force in the system, if you assume some kind of uncertainty within the force grain level, then even perfect collisions with this uncertainty would lead to an increase in entropy if you reverse time.
Yeah, but that argument, we're off topic here, but that argument will self-destruct, because you end up with as soon as you're talking about, you're making assumptions about the range of initial states, and that's going to end up being something which is essentially about state preparation. It's a little bit different. Coarse graining affects state preparation as well as state observation, and that what you're saying there is, I mean, it's just like state preparation version of the second law of the problem with the second law of thermodynamics is there a way that we can arrange the molecules of gas in this room so that they'll all go to one corner in a minute, right? And we argue we can't do that, and it's the same statement as the what's that?
The system is unstable, but much.
I think that's not the main point. The main point is do the computation. Actually do the computation to figure out how to get those molecules to arrange themselves so that they will go to that corner. That's irreducibly difficult. And by the way, if you succeed in doing that, go down to the level of the atoms of space and figure out how they're going to arrange themselves, and then you can travel faster than light.
I do think, okay, I do think Sotiris raises an interesting point though, right? Which is, so, I mean, to rehash the kind of NKS explanation, which I know is, itself a kind of rehashing of earlier stuff that you've done on the statistical properties of CAs and things. But, so if one views second law of thermodynamics as being essentially a cryptographic or cryptanalytic statement, right? That essentially, even if you have perfect reversibility, because of computational irreducibility, the action of the system can effectively encrypt details of the initial conditions to an arbitrary extent. Therefore, turning that on its head, if you as an observer are computationally bounded, then you're only ever going to be able to talk about equivalence classes of initial conditions and equivalence classes of possible evolutions and so on, which is the coarse graining point. So Sotiris, you then bring up the point about, well, what if your coarse grainings themselves have an element of uncertainty to them, which is, I think, a kind of meta version of the observer theory question, which is the observer is computationally bounded, but they don't know how computationally bounded they are. What conclusions can they draw? Which I think is quite an interesting question.
Okay, yeah, that's a reasonable question. Right, maybe we've almost exhausted the set of things we can talk about here. But is there any other, another thing that we probably should wrap up and continue this another time.
I have one other weird comment I want to make about chemistry, in case that's reasonable. Which is one place where I think weirdly there's a very direct connection to some very abstract pieces of mathematical physics. This issue, this question about chemistry and reactions between species and so on, turns out to be very, very mathematically similar to the question of D-branes in B-mode topological string theories, which is something I don't understand the physics of in any sense. But mathematically, what's going on is you've got these D-brane things, which are just objects in some triangulated derived category, and they can effectively.
Where did the category come from? They're things in string theory.
Right. As I say, I don't know what they correspond to in string theory. I'm also not entirely convinced that string theorists know what they correspond to in string theory, but you know, as I say, mathematically, you can treat them as objects in this category that's effectively like it's a triangulated category, which means it's kind of you take some infinity category and you kind of collapse it down to a one category in a way that you have some nice properties of the homotopy fibers. But
just my understanding is a string is this, you know, one-dimensional thing that traces out a world sheet over time.
Yep.
And string theory is the story of you know, is variational principles on that world sheet.
Right. And so the point is, in a topological string theory, that we're back to the functorial QFT case, right? The initial and final strings are like the initial and final states in the FQFT, and the world sheet is the cobordism relation between them. So again, they naturally define some category.
Now in the D-brane case,
yeah,
what's happening is instead of this one-dimensional string,
you've got some higher dimensional brain.
Higher dimensional brain.
Yep.
And so all that's happening is that you're looking at this, you know, relation, which is, as you're describing, cobordism relation,
right,
between the initial D-brane and the final D-brane.
Exactly.
And okay.
Yeah. So they form objects in this triangulated.
Concrete in all these categories. It's the cobordism between these D-branes.
But anyway, so these D-branes can merge and they can split in various ways, right? And so in particular, so they can merge into effectively something like a direct sum of D-branes, but it's a direct sum with interaction. That's kind of a bit like a semi-direct product.
String field theory.
Yeah.
Right. You're having the whole point of string field theory is that you have all these different ways in which the strings can split and join. And you have this, instead of having this, you know, plane surface that is the world sheet, you have this thing with all kinds of holes in it and so on.
Right.
And I assume there's a topological version of that, which I don't really understand, which is a topological quantum field theory related to string theory.
Exactly. Well, that's what topological string theory is. Right?
Oh, okay.
Yeah. So,
Okay.
and so, anyway, so then there are specific, mathematically, those, you know, if you've got, you know, D-brane A and it splits into a sort of direct sum with interaction of D-branes B and C, mathematically, in the derived triangulated category, although that corresponds to a homotopy, essentially a homotopy fiber sequence of B to A to C. And so then there's a set of purely mathematical principles, which I think are called the Bridgeland conditions on that category, that tell you effectively what, you know, which reactions are and are not permissible, right? You know, in which situations will you get fusing? In which situations will you get splitting, etc. And you can associate various different triangulated categories with different sets of Bridgeland conditions. And formally, it looks very, very similar to essentially this description of, like, you know, what reactions between chemical species are and are not permitted. And if that's true, that's quite interesting, because now suddenly a lot of that, you know, the mathematical apparatus that we were talking about earlier, that comes a lot of it from topological field theory, where you can actually talk quite explicitly about this duality between multi-way fibers and foliations. You can now wheel that in and essentially solve a whole bunch of, or translate a whole bunch of these concepts in chemistry to the same formalism. So there's a weird kind of, I don't know. I have this.
You know, I think, you know, Feynman diagrams are also not completely unlike chemistry. But what you're dealing with here is something where, you know, in string field theory, you could imagine a Feynman diagram like representation of string field theory.
Right.
And so this is something, although it is a little bit more complicated, because in Feynman diagrams are a story of particles, and these things are a story of more general objects that aren't just localized things moving one-dimensionally through time.
Right.
And so that's a more, you know, so that's a generalization of that. Now, whether in chemistry, it's a meaningful thing to have these more extended objects in space-time. I mean, I would imagine in molecular biology it might be. In molecular biology, it could be that in molecular biology, I mean, it matters that molecules are big in molecular biology, whereas most of the time in ordinary chemistry, in gas phase chemistry, for example, it doesn't matter how big the molecules are. They just, you know, molecules just float around freely, and every so often they collide. The collision frequency is comparatively low. In solid state chemistry, you know, they're just locked in place and they only know about their neighbors. Liquid state is the reason. That's why, you know, the airport security people are concerned about people bringing large amounts of liquid. That's where chemical reactions happen in a significant way, because there's enough density to have significant chemical reactions and not but so the liquid state case, is, let's see, what was I going to say? I lost my train of thought. Mads was
I have a question about the both of you about what Pierre was. Given this new paradigm to do science and search for intelligence, what are the potential physical phenomena or physical systems that we might be able to see a clear distinction between the conventional science and this new paradigm of scientific approach that you guys are in? Do you think that in near future there will be a place or an experiment, then one can say, look, this is the fingerprint of this approach that is not explainable by the conventional science?
But I mean, look, the most immediately applicable one will be a formalism for practical multi-computation. That is, distributed computing, which has been hard. That hopefully this formalism will give us a way to think about that makes it much easier to understand and much more accessible to humans. I mean, then there are a whole list of other areas between, economics, chemistry, molecular biology, immunology, linguistics, machine learning, neuroscience. I'm counting on my fingers, but I don't actually know the number that we've enumerated so far. But each one of these fields for different evolutionary biology, each one of these fields for different reasons, it looks promising that one can use this kind of multi-computation approach and potentially derive. I mean, the main thing that's going to happen is that in the world of computational paradigms, one's face to face, one's faced with computational irreducibility, so there's a limit to what one can say. In the case of multi-computation plus observers, the right kind of observer can find general laws. The only problem is, what kind of observer is that? And for example, let's say in economics, or for that matter in chemistry or molecular biology, it could be the case that the observer that we have normally been using is one that can't find a global law. But there is an observer that maybe some other kind of observer that measures different kinds of things in economics or neuroscience or whatever. That other kind of observer can find global laws. And that other kind of observer, it could be that you just go right out and measure such and such a weird thing in economic systems and say, my gosh, the economists who've been trying to find global laws for years, and everybody thinks or many people think they haven't really found anything. Maybe, as soon as you measure some different bizarre thing that you could measure in a virtual world, you could measure some detailed thing about correlations between, amounts of money went here and there, suddenly, boom, there'll be a global law. That's the type of thing that I think will happen.
In relation to your question about potential experiments and things like that. So I think it's important to make a distinction between sort of paradigms and theories, or meta models and theories, or however you want to formulate that. I mean, so in a sense, it's very directly analogous to the distinction between a formal model of computation and a specific computation, right? So in a sense, a scientific theory is like a specific computation. It predicts that the output of such and such a thing will be X. And if the output is not X, then your theory is falsified. And that's kind of, so individual specific computations and classes of computations, that's what the whole, Popperian, Kuhnian, et cetera, philosophy was kind of set up to deal with. With something like multi-computation, or I argue even with the original formalism of the physics project, I don't think we were ever talking about theories at that level, right? This is a formal model of, I mean, in a very concrete sense, multi-computation, hypergraph rewriting, all these things are formal models of computation. They are a kind of space within which you can embed theories. They are not themselves theories.
Although,
so that,
good at that.
Okay, so, but there is an important, so there is a sense in which you could sort of imagine falsifying a paradigm, but the distinction is much less sharp than it is for ordinary theories. It's because it's ultimately one of aesthetics, right? So in a sense, what's actually happening is you've got these computations that correspond to your models, and you've got the computations that correspond, we think, to actual processes that occur in the universe. And the basic problem of theoretical science and observational science is to essentially define some kind of encoding function, some intermediate computation that lets you translate between abstract computational states of your model and concrete, physical, natural states of the system you're trying to construct the model of. And so then the strength of a paradigm lies, I would argue, in the simplicity of its encoding functions. A good paradigm is one where you can write down encoding functions that have very minimal algorithmic or computational complexity. And a bad one is one where the encoding functions have to be extremely convoluted and contrived. And so in a sense, you could imagine falsifying the multi-computational paradigm if you could find an example of some system where, yeah, of course, because of universality and so on, it's possible to construct some simulation of it if your encoding function is allowed to be arbitrarily weird and contrived. But, if it were the case that, for instance, with the physics model, you can reproduce general relativity, you can reproduce quantum mechanics, you can reproduce quantum field theory very naturally, as appears may be the case. But to be able to reproduce the mass of the muon or something, you require some big 100,000 line program. That's a sign that it's not a falsification, but it's a weak point of the paradigm. And so it's as I say, I think ultimately it's your question is one that requires in the end a kind of aesthetic judgment rather than there's no sharp distinction, I'd say, when you're reasoning at the level of entire models rather than at the level of specific theories.
But it's also like the question of, could calculus be wrong? The answer is that's not the right type of question, because calculus is just this formal setup. And calculus could be irrelevant to things in physics or things in the world, but it can't be just wrong. So that is,
Right, but that comes back to the encoding function thing, right? So calculus, as far as we can tell, is a sort of universal paradigm for doing math. In principle, you could do combinatorics with calculus if you set up some weird combination of step functions and you used integrals to count things and whatever. But it would be horrible. Like no one would want to do that. In effect, the encoding function would be really, really complicated.
You could do set theory with counter arithmetic.
Right, exactly. Yes.
So,
yeah.
So it's some.
Yeah.
Right. No.
But why would you? Yeah.
As a matter of fact, in calculus, you can't have paradox like measure theory. You're not very careful when you start building some measurable sets. You would get some paradoxical behavior. So
it is an interesting question whether a paradigm can have paradoxes and whether that is a sign of what the heck that's a sign of.
See, I would argue paradoxes, again, they live at the level of the interpretation. They live at the level of the encoding. They don't live at the level of the underlying model, I would claim.
Paradoxes.
Well, there's an interesting question of whether the Rule-Iad is self-interpreting.
What's that?
Well, so if one makes this distinction between computations and the kind of interpretation of the encoding of their semantics, does the Rule-Iad contain its own encoding function? And
the answer.
Sorry?
At some levels, yes, but it depends on what the observer picks out of it. In other words, it formally contains what the observer does, just as any universal computer formally contains the encoding of, any encoding of that universal computer.
Right, but it's not necessarily instantiated.
Yes, but in the Rule-Iad it is instantiated. Right.
One would assume. Sorry, Mads had some interjection, which I didn't hear. Oh, sorry.
Yeah, go ahead.
yes, for example, let's take the classic example, the task paradox. In what sense would you say this is a matter of interpretation, if not matter of the model? It's a nice example.
Well, because again, if you go back to proof theory, so Banach-Tarski is about a specific model of general topology. It's about a model in which, well, ultimately, well, I mean,
So you can take apart a ball, you can reassemble it in twice.
I don't know. Measure theory is topology with an additional function that. Anyway, but well, no. So all I'm saying, yeah, it's based on a proof. I think the place where your confusion may be coming in is that it's based on a proof theoretic thing, right? Which is the fact that if you allow axiom of choice, you can have, as you say, non-measurable sets, and one of the consequences of that is, if you have uncountable choice, I should say, that you can have the Banach-Tarski paradox be true. But it's a paradox. The paradox makes reference to particular balls, right? It makes reference to an actual semantic mathematical structure. It's not a proof theoretic statement. So again, I maintain the paradox exists at the level of the encoding. It doesn't exist at the level of proof theory, right? Similarly, Russell's paradox is a statement about a set. It's about a model of set theory. It's generated by a proof theoretic problem with set theory, but the way that the paradox is actually formulated involves you having some kind of semantic interpretation for the underlying term.
Let's go through this. Well, let's take a favorite paradox. Should we take Russell's paradox, or should we take Banach-Tarski? Which is the right one to?
Well, Banach-Tarski is based on a much more sophisticated formal system.
Okay.
So I think it's probably easier to analyze the simpler case. But
Okay. So can you?
We don't say it's part of calculus, but please be a better example.
What's that?
We also say that it's part or close to calculus, but I think that's a better example.
Right. Maybe these guys should comment because
Aren't we, if I understand Jonathan correctly, then aren't we essentially making the statement that if you have one Wolfram model where relativity holds, but some cosmological thing contradicts itself, so it cannot be a physical model, that's not evidence against Wolfram models in general as formalism. Whereas if all Wolfram models had the shortcoming that they couldn't predict something in reasonable effort, and you would need to add lots of unnecessary complexity, that would be a criticism against the paradigm itself or the meta model.
just like
that's yes.
And I think it's the exact same thing with, I don't know if that rephrasing it.
Yeah, no, I mean, and it's the same thing with calculus. Is calculus useful? And it seemed to be for the last few hundred years. That's
I want to go back to Fonz's question. I think it's actually a much more straightforward question that we've kind of answered somewhat evasively, which is, I don't think Fonz is asking, will multi-computation be proved wrong or not? He's asking, can this overall paradigm, will that lead to us positing new theories that could be, confirmed with empirical or experimental, evidence? I think that's going to be true. I mean, with economics,
Definitely.
for instance, we have some global law of economics. We could actually test that out, and if it's right, then we'll do very well. I mean,
Right.
or whoever tries that will.
well,
do
we've
very
also
well.
got global laws of mathematics that we're talking about,
Right.
which are
I mean, look, with molecular computing, if molecular computing works well, we actually have some, we understand how it works, we should be able to make a molecular computer, for instance. With physics, I mean, this is something that we want to do at the Institute, because we want to actually bring in experimentalists. So we have to design experiments that we think can actually verify.
Yeah, it's really a shame. There's so many experimentalists that contacted me and said, just tell us particle accelerators, telescopes, you name it. What should we do to
To justify some grants, so give us even excuses to run.
Well, yes, you give us new experiments to run, but I think that's why several projects at the summer school have to do with things about photon propagation through fractional dimensional space and things like this, because that's where we can tell some person with a telescope, so to speak, go look for this absolutely bizarre form of gravitational lensing, and that will be something you couldn't possibly have seen in interdimensional space, for example. That would be a nice effect.
I think there are three things that we can do. One is we can build up the overall paradigm. We can also do what Jonathan was suggesting, which is there are existing theories. We see how we would model those theories, and we can apply,
Fancy stuff.
we can
to
do
those
kind of
things.
Occam's razor, comparisons of our how we model it versus how other people model it. And we should also have new theories, and those will be tested out experimentally. But also when what we do relates to things like technology, like distributed computing, I mean, solving problems in industry as well is a perfectly valid, kind of experimentalism, I think, as well. So all three, building new paradigms, comparing our models with other existing theories, and doing new stuff.
Yeah, I mean, it's also interesting that some of the kinds of science that we might have things to say about are not really natural science. They're things like economics, linguistics, areas, metamathematics. These are areas that are not traditional natural science. So they're areas where it's observations rather than experiments. Same with the evolution of biology, as observations rather than experiments. So it's a little bit of a different thing. The Popperian model of how science works is exceptionally narrow, and it's really a very physics-based idea, experimental physics-based idea. I'm reminded of when I worked at the Institute for Advanced Study. There was this older physicist who was, I would not say a great friend of mine, but who, when he had first, he was an astronomer, and when he first come to the Institute, he was telling me the story. He'd met Kurt Gödel, who was there, and this guy had explained with great enthusiasm all this stuff about how he was studying star clusters and all these kinds of things. And Gödel had said, "That's very nice, young man, but I do not believe in natural science." So, so you can see the Platonic, view of, I mean, it's interesting. He says he doesn't believe in natural science because he has this ultimately Platonic view of everything. And this,
Yeah, but even Plato said that the real world is a shadow of the ephemeral. It starts with actual science.
I think
Yes.
Penrose has it right with this triangle that the physical world creates the mental world creates the Platonic world, the Platonic world describes the physical world.
Penrosian trialism as opposed to Cartesian dualism.
But I think we should be able to have it kind of both ways in some sense. On the one hand, if we're able to understand ourselves as observers, if we're able to do, if we're able to find applications of multi-computation that seem to be accurate, whether it's through observation or through other industrial applications or whatever, that kind of helps to buttress and validate this particular paradigm. But on the other hand, as we get farther into the Roolead, so to speak, when we're doing Roolead motion and there's like some coordination of the Roolead, I mean, part of those pockets aren't going to correspond to anything in our world whatsoever, right?
Yeah.
But if it seems as though we have authority over our domain in the Roolead, and that seems quite solid, then people will have to take some leap of faith that you can also use this paradigm to explore things beyond what we have access to. But if we don't have any authority over our domain, then it will all seem to be somewhat speculative. If we do, then someone will have some faith that this applies more generally, that's what will make it very interesting.
I'm going to interpret Sotiris's comment as a conjecture that Plato's form of the good is actually a veiled reference to the Roolead.
Yeah,
It's how we illuminate all other computational structures.
yeah, right. It's nice. I mean, this is in there. There are no new ideas under the sun. In addition to Plato, we go to the theologians and all this kind of thing. But this whole point about, the role of science and the role of us in science is interesting because, in a sense, it could be the case that to make progress in science, we simply have to understand ourselves more. Because that's the story of it. If the Roolead is just out there, and to know what the science as we perceive it is, we have to understand more about how we do the perceiving, as much as we have to look outwards into kind of natural world.
I'm going to disagree with you there a little bit. I mean, as we've discussed before, and I think has come up in other conversations. I mean, my view of this is more like you as the scientist have complete freedom on where you place the computational burden, right? The traditional case that, as you discussed in NKS of you assume the observer is infinitely computationally sophisticated relative to the system they're observing, that effectively corresponds to the situation where, if you like, the observer's computation doesn't matter at all, and all of the dynamics is going on in the computation of the system. The Roolead picture is, in a sense, the system is doing some trivial thing, trivial in the sense that it has basically no algorithmic complexity. It's just all possible computations occurring in parallel, and all of the burden is shifted onto the observer and how they encode things. But I would argue that, in a sense, you have freedom to choose either of those extremes or anywhere in the middle. And so I don't think it'll ultimately be the case that if you make that selection, that you'll end up being forced to learn more, to encode yourself as an observer to a greater or lesser extent than you initially had to begin with.
No, but I think the point is that if we were sort of utterly trivial observers, the fact that we are observers as we are means that our sampling, we are taking a certain burden in your picture as observers. And the burden that we are taking is causing us to perceive things the way that we perceive things.
Yes.
If we were taking a different burden, if we were different from the way we are, we would perceive different things.
Mm-hmm.
And so to know what we are going to perceive, we have to know some characterization of how we are, so to speak, which is not something that science usually discusses. Well, it actually has discussed many times, right? To know, relativity is the result of being realistic about simultaneity. Quantum mechanics, the result of being realistic about, well, some kind of measurement thing.
Right.
You know, so it isn't the case that science has never had to confront this thing about what observers are like. But I think what we're realizing from this Rulliad picture is that there's a much more of a spotlight back on what are we like as observers.
But again, I would say that's really the kind of whole algorithmic complexity aesthetic encoding thing, right? My conjecture would be that yes, general relativity and quantum mechanics are elegantly formulated if you are realistic about the limitations of the observer, which we agree upon. But you know, the counterclaim would be that there would be scientific theories which are observationally isomorphic to general relativity and quantum mechanics, which assume nothing about the nature of the observer, but which are much more contrived to specify.
Yeah, it's just a Turing machine.
Right.
It's all good. I mean, you know, then you have everything. I mean, then you can construct everything. It's just not. It's an observer of immense complexity that's needed to go and, you know, construct the Turing machine that constructs the universe, so to speak.
It's just a Turing machine. It's all good. Should have been the subtitle to NKS.
Well, I think that I mean, this question about Rullial jumps and what happens, you know, we live where we are in Rullial space, what it's like elsewhere in Rullial space. This is why I keep on obsessing about this animal communication stuff, which might seem irrelevant, but that's, you know, that's a case where we actually have a different place in Rullial space, so to speak. And you know, I don't know, it's I mean, and the other example is in Rulliology, where we're just jumping to some random place in the Rulliad, and where we have no current, you know. And I'm curious in this whole categorical view of things, right? To what extent, where does the observer picture come into this categorical view? I mean, in other words, where does the observer enter the categorical view? And if we jump not through hyperspace, which is old science fiction, we jump through Rullial space and we land somewhere. Maybe that's what Rudy's science fiction story, which I haven't yet read, is about, is jumping through Rullial space to somewhere else. But anyway, if we jump through Rullial space to somewhere else, we land in this utterly alien, you know, world that is not described in the same way that our world is described. Can we still have category theory?
Right. I mean, well, in some sense, that functoriality is a version of that idea, right? Functoriality is a version of Rullial translation. You're saying, you know, the semantic interpretation of everything we're dealing with is completely different, but the underlying compositional structure of our computation is preserved, and that's, you know, that's at least one form of Rullial translation. But and then on a potentially more interesting level, you know, one way that you can reason towards the Rulliad, so to speak, is, you know, you take this model of multi-way systems as monoidal categories, and these towers of completion procedures, which you can do to effectively populate an entire Rullial space, you can code, you know, as is discussed in stuff by Xerxes, myself, and Hatem. You can encode those completions as the introduction of these higher homotopes or these higher morphisms, and so on. And so eventually, you know, you reach some point where, in the end, you obtain some infinity category that is the sort of full Rullial multi-way system. And then, I don't know whether it's the hyper-Rulliad or the ordinary Rulliad or something, there's then a classifying space of those Rullial multi-way systems, which is given by some infinity one topos. And then the role of the observer is that they are some sort of principle by which you can take that, either the initial infinity category or that infinity one topos, and you fibrate it in some particular way, in such a way that the multi-way systems or Rullial multi-way systems that you obtain by taking some global section inherit some nice features of the overall infinity category or infinity one topos. For instance, something like spatiality it would be a common form of inheritance.
So what you're basically saying is, what fibers of aliens are likely to be understandable? Right. So you're asking the question of what, I mean, this is the SETI question, basically, is in the expanse of Rullial space, you know, where are we likely to find, you know, aliens that we can understand? Mm-hmm. And how dense is the set of aliens that we can understand in Rullial space? And is it a set of measure zero in some sense in Rullial space of aliens that we can understand relative to not? And you're saying, you're describing this selection in this infinity one topos, so to speak, of things that have certain properties like spatiality. Right. So prove whether the set of aliens we can understand is a set of measure zero.
Well, so my hypothesis about that, again, it's getting very speculative. It's similar to the speculations about chemistry, is that essentially, okay, my philosophical perspective on that question is that you need that there's that beyond us if you're outside a very narrow domain of shared cultural experience, communication is impossible because it's essentially the computational equivalence thing, right? It's indistinguishable from essentially thermodynamic noise. And my operative hypothesis has been, when thinking about this, that essentially a way you can encode shared cultural history is through the causal structure of the Rulio multi-way system, right? So effectively,
Yes.
the fibers over which you can have effective communication are those that have sufficient shared causal history in the event structure. And if you've got fibers that are completely causally disconnected, then communication becomes theoretically impossible for essentially reasons that are not dissimilar to sort of event horizon type arguments, right?
It's also saying the Rulio space, because there's a Rulio graph, just like there's a branch graph, and you're saying that you're distant in Rulio space.
Right. And there's a certain level of distance beyond which, essentially, your past causal ancestor is far enough away that, communication becomes
Past
impossible.
the Big Bang.
Right.
That would be one possibility.
Right.
That you're actually in disconnected regions of Rulio space, and then you're totally toast. Then the aliens in disconnected regions of Rulio space are truly gone. They're truly separated. But I think this, let's see, I was just going to comment, just a side cultural comment. I mean, for some reason, this is the year of growth. It seems like, everybody's talking about growth. There was an article in the New Yorker, there's this person, Cormac McCarthy, who's writing a novel that has a big growth and like character in it and so on. And I'm trying to understand why, and that's the world of infinity categories and things like this.
Yes.
And I'm just trying to understand from.
Sorry, some of us didn't get it. You're talking about what?
Alexander Growth.
Alexander Grothendieck. There.
Part-time wizard.
I'm probably pronouncing it. I don't know. Can anybody pronounce Grothendieck in its native?
Alexander Grothendieck.
Grothendieck. Okay. All right. Closer. But I'm just wondering whether some of his thinking about the infinity category, infinity groupoid, and so on. What more can we mine?
Well, that's the comment I was making about spatiality, right? As you know, so in effect, Grothendieck had this idea that what one kind of abstract model you can give for topological spaces that doesn't require you knowing anything about points or whatever is to model them as infinity categories. And the reason for that actually is very interesting. I mean, it's kind of intuitive it sounds really weird and abstract. It's kind of intuitive when you think about it in the right way, which is what you're saying is, okay, so you've got some topological space. You can look at paths in that space, and you can look at homotopy between those paths, and you can construct then a homotopy space where the points in the homotopy space are paths in the original space, and the paths in the homotopy space are homotopies in the original space, and then you can construct its homotopy space and so on. You get kind of this large tower. And so in the categorical interpretation of what's going on now, points are just objects, paths are just morphisms. Now this gives you a way of constructing an arbitrary infinity category. And we know that for homotopy spaces, there's at least a large class of cases in which if you know the infinity homotopy space, if you know the infinite limit of this picture, then the structure of that infinite, the infinite limit of this homotopy tower determines. Once you get to the infinite limit, something really rather remarkable happens where the structure of that space determines the structure of all the spaces in the hierarchy below it, at least up to weak homotopy equivalence. And so then Grothendieck basically took that and took that idea. So if you construct the infinity category that is the infinity homotopy space for some topological space, it determines everything that you as a topologist might reasonably care about not just the original space, but also all of its higher homotopy spaces. He took that idea and he just took it to its logical conclusion. He said, well, maybe it's not just the case that every topological space is modeled by an infinity category, but maybe every infinity category can be thought of as a model of a topological space. And so maybe an abstract definition of what a topological space is up to weak homotopy equivalence is that it's an infinity category of some description, which then motivated a lot of this work on trying to classify infinity categories and infinity groupoids and all this kind of stuff. And so in the Rulio picture, and this again is an insight that's really originally due to the Xerxes, but one question you can ask is why do so many of the structures that we encounter in the physics project, like causal graphs, hypergraphs, multi-way systems, etc., have spatial interpretations as Lorentzian manifolds, Riemannian manifolds, projective Hilbert spaces, etc. And one perspective on that, which is the kind of Grothendieck perspective, is that you've got this Rulliad that has the formal structure of an infinity category, so it is naturally spatial, it is naturally a topological structure, then you take an appropriate global section, and if you take those sections sufficiently judiciously, then those sections effectively inherit spatial structure from the Roolead. And so one reason why we have, one possible explanation for why we have spatiality in physics is that it's spatiality that's being inherited from the infinity groupoid structure of the Roolead.
Although observers like us, I mean, I claim that spatiality is a feature observed by observers like us.
Right. Well, I agree, but that's where the phrase "up to weak homotopy equivalence" comes in, right? So the spatiality. So up to weak homotopy equivalence is really a statement about observer coarse grain.
Yeah.
Right.
Right. Which is also a statement about computational boundedness of observers.
Right.
And so weak homotopy equivalence it's all the same story.
Yep.
And so we observe space because So I mean, there's this. I'm just so curious to understand something. In a sense, the growth of knowledge is an expansion in real space. And I'm sort of impatient to jump to a different place in real space and understand what's out there. And as seen by, but of course, then we have the problem of the communication between, it's, I have to say, I'm reminded of, sadly, a thing in the 1950s when people were first talking about cybernetics. Okay, there's this big proceedings and so on, and there's one of the core articles in there is called "Communication Between the Sane and the Insane," which is kind of it could be a version of this kind of real thing. In those days, the notion of these things was a bit different. All right, we should probably wrap up. Many things that could be followed up, but we can go to that. I have no idea.
Thanks very much.